Good afternoon, everyone, and thank you for joining us for our tutorial. I'm very excited to be here with you. So let's get started. My name is Oren Aiden, and I'm going to be one of the presenters of this tutorial. I'm an assistant professor at St. Louis University.
Good afternoon, everyone. I'm Felipe Diaz. I'm with the Oak Ridge National Lab. So I'll be also one of the presenters today. We're going to be covering this agenda that Oren is going to detail a little bit now.
I think everybody had enough of our dynamic header. I think you looked at it a million times already. So I'm just going to scroll down a little bit and assuming that you've taken a look at the overview since you're here, just talk a little bit about our schedule and what to expect. We will quickly introduce basically what we're going to cover today in our opening statements. And we're going to start talking about Earth observation data. And I'm assuming that you're aware that there are a lot of great Earth observation sessions, tutorials that are either happening right now or about to happen. And we want to focus on the data first. What do we measure? How is this different than some of the other types of computer vision data that we're working with? So to really set the stage first with the data. And we're going to have a small hands-on section. And if you go to that link, that links to a collab. So with this tutorial, all batteries are included, so to say. So you can just go to this collab notebook, launch it. The only requirement that you need to have is an AWS account. It doesn't need to be like a premium account. You just need an AWS account if you want to follow the clicks. But if not, you can still follow along in the notebook, and the notebook will be there for your reference. We're going to have a coffee break and unstructured Q&A. What's going to happen there is if you are following along the notebook, but if you want to explore some other options, if you have questions specific to this notebook, I will be here. And also one of my students who's supporting this event, Donovan, will be here to answer your questions so that we can answer any like data IO related questions one-on-one. And after this first half, we will start talking about machine learning methods, machine learning tasks. How does it fit into the data that we discussed? Talk about foundation models, and going from models, talking about applications. What does this mean for sustainability? What does this mean for resilience? And we will talk about some hands-on examples, applied examples. And we will end with some remarks and an exit survey. I know nobody likes surveys, let alone exit surveys. Because that generally stands between you and the exit door. But it'll be very helpful input for us to make this workshop more tuned to the needs of the community if we do this again next year. So with that being said, we will get started.
Jump to the slides here. So let me start with a question. How many of you knows what is Earth observation, what this is useful for? Did you have? Okay, so just start with that. You know what this is useful for and you're curious about it and you're here to learn more. Great. How many of you have any experience playing with this data, like getting your hands dirty a little bit? Seems to be about half and half. So that is still within our expectations. So myself, I have experience with this data for about almost 4 years now. So I come from more conventional electronics engineering background, computer vision, that since 2015-ish, 16 has been dominated by deep learning and so on. Kind of follow that trend, but also more working with the Oak Ridge National Lab with what we call application-oriented type of research. So that includes parts of like, how do you select your data? How do you do the labeling, do the training and deploying of our models, but also some post-processing and assessments of quality and so on. So those are some of the things that we're going to be touching, particularly at the end, when we talk about this type of real world usage of these things. Some of these steps beyond of just training and deploying your model for a single image, so to say. But we start, what we want to cover is giving a little bit for those of you that maybe are not familiar yet, very new to the Earth observation type of data. What we're talking about here is essentially this idea of gathering information about the physical, chemical, and biological systems of the Earth. And in particular, this idea of remote sensing is very useful for scenarios like you cannot simply go to a certain location, like in the middle of the Arctic or the middle of a desert or the middle of a disaster scenario, and try to take whether photos in like the street level or getting some other sensors. So having this ability of leveraging satellite or aerial imagery by an airplane, so like doing surveillance of the place, can be very informative for responding like to disaster scenarios or doing more of this kind of larger scale assessment of these features to guide policymaking and so on. So they has a lot of applications that can range from agriculture, disaster response, urban planning, humanitarian assistance, and so on. I start these examples here with some of the work we do at the National Lab, which is working with a lot of folks from the geospatial side, whether intelligence or population modeling, that you want to understand where you have maybe constructed areas, where you have buildings in particular. You can think of, well, population, you already know the census of a location, but that gives you just an aggregated information at a very high level. If you want to have a more fine-grained estimate of where population are living and maybe do that of more finer temporal resolution than just relying on a census every 4 to 5 years, that can be a very informative proxy that you can then aggregate with other types of geospatial data and construct this kind of very high resolution mappings of population across entire countries or even the entire world, as we've been doing, like with the Landsat project everywhere now. And then you can go beyond that and look as well at road mapping. That is very important when you think about transportation networks. You can think of scenarios like flood, let's say what areas have been blocked or not, so you can think about aid going to these locations. And you can think about more fine-grained attributions of, for example, the buildings. Try to understand whether something is being used for commercial purposes or residential purposes, because that can be very informative for folks more like from the geography side to understand maybe the wealth of a certain area or what are the risks and vulnerability assessments and how you can start to think about policy making around those features. Some other very interesting applications are more around environmental or land use understanding. Land use and land cover classification is a very classic problem in this domain of computer vision and earth observation. You can think of things such as understanding where you have areas being used for agriculture or areas being more urbanized, the level of urbanization, and then start understanding over time patterns of deforestation or what areas are getting more densely populated and so on. And in particular, I think these types of works on disaster response is a very rewarding space to be working on, and well, it's unfortunately will be more and more important when we think about climate crisis scenarios and the ongoing conflicts we have around the world. There is increasing frequency and need for this type of mappings in ways that you can, as fast as possible, provide information to people on the ground doing humanitarian assistance, or also thinking about accountability purposes in some other scenarios. Other scenarios you can think as well is trying to map maybe populations of features that are unseen, so to say. You might have maybe some volunteer-based information like OpenStreetMap that for some areas people can go there in this sort of open Wikipedia and select where you have features like schools. But these tend to be sometimes incomplete. So you can have works that leverage satellite imagery or types of imagery, computer vision techniques to actually shed light on these structures that are unseen, so to say, mapped. And a lot of work more on conservation and so on. If any of you were maybe in the morning in the Earth Vision session, there was a great keynote talk talking about how computer vision and machine learning in general pair with EO data already plays a big role and will continue to play a lot of role in trying to understand these aspects, such as compliance with regulation of the usage of the land, where you have some maybe illegal plantations, or you can also have this work like it was done recently a few years ago by NASA and finding vegetation where sometimes you wouldn't be expecting, so to say, to see, like what you have in the Sahara and the Sahel. And this kind of information can be relevant when we think about not only sort of deforestation, but also thinking about overall the carbon cycle, and also those risks that you might have, or maybe how much fuel have in certain area for wildfires and so on. Similar again here, this aspect of trying to conflate mappings of one type of vegetation and what should be the information you have from maps in terms of regulation. Other types can be more around wildlife monitoring as well, which is a very illustrative example of how hard it can be to play with Earth observation data. It's not that nice picture of your cat in the very center of your image, like you see in those image nets and the like. Things get much more complicated in terms of scale, distribution, and so on. And all of this that I show was mostly just with RGB. Things are not only RGB. Things can be radar, for instance. I'm going to detail more how radar can be more advantageous compared to just optical imagery. But this is one example of one challenge, the XU3, that was 1 or 2 years ago on trying to map illegal vessels. So these are vessels that sometimes they are not emitting what they should be in terms of communication by radio, and they are maybe fishing in zones that they shouldn't be fishing. So it's a very hard problem to actually have some monitoring on what's going on. And plenty of other applications that we can think beyond just this imagery part, but also understanding climate patterns of whether you have, what is the forecast of certain features, or also this idea of super resolution. You can think of it helping getting finer grained maps as compared to coarser maps that you would have constructed from other sources. So all in all, one of the things that we're going to discuss is how there are many analogies that are some categories of problems that from the broader computer vision, that they are still here in the Earth observation, but there are plenty of extra challenges on how you handle those. So those are some of the things we're going to cover in this tutorial. We don't have the time in half a day to do everything hands-on. So we're going to have a hands-on session in particular, like how you can use this type of data and start to play with it. But then we're going to try to cover many bases of resources you have available that you can search out there, data loading, visualization, processing, the types of techniques used for each of these problems, the extra tweaks that people do, and so on. And then the other thing that starts to be fun to think of is like these extra challenges. I mentioned that it's not only RGB. So you start to have issues even if you're just dealing with the RGB, with the optical. Spatial resolution can change a lot. You can have images from certain types of sensors that each pixel corresponds to maybe 0.5 centimeter, which is a great image to work with for satellite purposes. If you're working with an aerial, maybe you're going to reduce to tens of centimeters and so on. But then you also have sensors that you're then operating maybe 1 kilometer or 100 meters per pixel. And ideally, you don't want to be training specific models for each of those. So this generalization issue becomes a big problem. Or even if you have the same spatial resolution, your view angle might change according to the positioning of your satellite. And that can easily, again, break models that are just trained for one type of view angle. It can break even your mind too if you try to delineate the exact footprint of a building here in this view angle. It's a pretty tough problem, even for a human to handle. And then there's multiple differences in the amount of channels you might have from hyperspectral data and so on. So to illustrate just a bit further before we dive more into specifics of the data, I just want to show more examples of this contrast between the conventional, so to say, conventional computer vision data sets and the things we have to deal with. So here I have a series of examples that you're looking at the same area with this type of sensors. So you can see how it's more familiar to us, like the red, green, blue kind of thing. But then you can start to think that there are many features that can be interesting to start looking at the infrared, things such as more understanding better vegetation patterns. And how do you start to even like, how do I visualize those things? I can process as a human, like 3 bands kind of thing. So I replace my red by the near infrared, or what do I start to do? And then you deal with a bunch of code bases that you can start to use from the broader computer vision. You put your data there and you see that's not working because things are hard coded, assuming that you have 3 bands. Things are just not like this when you start to deal with other modalities. You have other types of data as well that you have some sort of combination of them, like the NDVI, this is a vegetation index. You start to aggregate information from different types of bands sensors in your spectrum to have then a better way to visualize and handle this data. And then you get to the fact that you have different sensors being better for different benefits or different disadvantages. One classic example that we have is this notion of optical and synthetic aperture radar. So when you think about optical data, that's what mostly we are used with. It's essentially what we call passive sensor. You're taking pictures that essentially is the reflectance of the sun illumination that you're measuring then, right? But then you can have issues such as cloud cover. So you are very interested in trying to get images and process as quick as possible for a certain, I don't know, flood event or wildfire that happened at a certain location. You get the image and then you look, it's pure cloud. And that's a problem that radar doesn't have because you have an active type of sensor. So essentially you are emitting pulses and measuring the reflectance. So this can be great for those scenarios where you need to assess changes as quick as possible. And you have these issues of like cloud coverage, in particular, like in the tropics. But you can see that it's a much harder type of data to work with. There are issues such as what we call the speckles. So you can see like this kind of cross in the middle. And there are issues such as like when you're measuring reflectance from the radar, you can imagine that you have different structures of different heights. They might reflect in such a way that a single point or pixel in your sensor is actually capturing reflectance from different parts of the surface. So that gets pretty tricky, even the physics underlying it, and how you can try to enable this kind of reasoning across these different types of data. Here's just another illustration, same location, different types of data, how things can look wildly different. So ideally, you would like to have a multi-model kind of model being able to handle that. And that's another thing we're gonna hit quite a bit today, that multimodality can come in different flavors when you look about this type of data. We tend to think nowadays of multimodality as a synonym for RGB and text, but no, you have multimodality issues that can arise from different channels, different spatial resolutions, temporal resolutions, so on and so forth. Points, pixels, many variations. I already covered this. I will let Orhun speak a little bit more to that, but essentially this aspect that you can have different sensors capturing, focusing different types of spectrum because they can be beneficial for different types of applications. And then I just want to hit on the temporal part because this relation between spatial and temporal is very important to keep in mind because you think of, well, we have these different resolutions of the sensor, so let's try to just use the best, the finest resolution you have. But that becomes a trade-off because to you to cover such fine resolution, your speed of how often you can actually get this, it's sort of inversely proportional. You have more coarser satellites that are going to orbit the Earth more frequently. So here is just a visualization of how, for example, for the Sentinel-2, that's 10 meter per pixel in average type of mapping, how it takes, how the orbit it's formed essentially for you to remap the entire world takes you about 5 days or so. And then you start to have already issues of you have this data maybe coming from different sensors. You want to be able to work with them. And the good thing about geospatial data essentially is that usually comes with metadata. So this means you know where was the location that was taken, the time, some features such as the orientation angle of your sensors and so on. But then you can have issues as well, different types of projections of how this data is coming. So if you just try out of the box to try to align things, one is represented one type of world representation, the other data is represented another way. And then how do you do project things to the same space and do this conflation such that you can do this type of multimodal reasoning becomes another tricky thing to do. So that's what I wanted to cover in terms of motivation. Hopefully you find all those applications exciting and you're curious to know how the hell you handle all these different problems. So we're going to start talking now about these more nuances of what you have with your data, how you, the relevance of these different types of sensors, and then in a few minutes start to get our hands dirty with actually loading some of those sources. That's what I had to start, and now I'm gonna let you guys before him. Thank you.
Thank you, Felipe. So let's talk about a little bit in detail Earth observation data. Some of the examples that Felipe show are very striking examples. There are all these different problems we can solve with Earth observation data. And when you go to, for example, USGS's data hubs to get, say, Sentinel data, one question you might have is, well, what is the data am I looking at? Is this raw measurement? Is this processed somehow? Because if you're interested in uncertainty, you would probably want to know those processing steps, the parameters, et cetera. And you may want to understand how, what the variation might be. So before going into, so I would like to talk about the details of this, and I want to start with really the basics of Earth observations, just to give you an idea of some of the key concepts. So one common terminology we use is whisk broom versus push broom. And this basically is an animation from NASA that I would like to quickly show. So when we have a whisk broom sensor, you will see that the sensor is not just getting a pixel at a location. As it moves, it's also doing a lateral scan. And all of those images are being mosaiced together to create this final data product. The algorithm behind processing whisk broom sensors is a little bit more complicated, but the equipment itself is, the sensors themselves are easier to use. And when we think about push broom, and you can really think about a broom here, you'll see that there is no lateral scanning anymore. We basically get slices of images as the satellite moves. So whisk broom, so not only you're moving forward, but you're also doing lateral scans, and that does impact data processing versus push broom. So those are two important things to think about. And in the final animation that Felipe showed, you have seen how these satellites are moving. So as they're moving, what we are basically doing is, for those of you who are very new to Earth observations, something that we've been doing for at least a decade now on our phones, which is creating panoramas, right? When these functionality first came out, you will take a picture of a scene and then you will slowly move it. Very much similar to this continuous data collection from a satellite to mosaic everything, to put everything together to have a global view. So there are a couple of concepts to talk about here. The first one is the swath. And again, this is from this animation. So what is the swath? Swath is basically this area that as you're moving that you can visualize with the satellite. So that's what we refer to as a swath. And this is particular to Landsat. A swath is about 115 miles by 1,710 miles. And we put these swaths together in the end to have a global image. So how long does it take? Well, you've seen this in the figure. Approximately for Landsat 8, we have 16 days. So in 16 days, we can create an image. That is also quite different than some of the image problems you work in, for example, with web page data. I'm seeing a lot of you taking pictures of this, which is great. When you take a picture of this, it's the same snapshot. It's not like one half of this board is from 2 days ago and the other half is from today, right? But when we look at global data, we have this issue. We don't have a synchronous snapshot. We can't, because we are obtaining this data in swaths. So in a 16-day revisit time, you're going to have this, higher than 2-week latency in certain parts of your data. So these are two important things to understand. Talk about this a lot, and if you're new, it's just good to have an idea of how to visualize this and what this means. And we talk about global observations. Again, remembering that the global observation does have this concept of revisit time. Felipe also touched on an excellent concept. He was talking about an active sensor, for example, some of the synthetic aperture radar sensors that we use versus passive sensors. For example, the Landsat data set, we work a lot with passive sensors. So what do we really mean by this? Again, I'm not going to be talking about any of the physical equations, but I want to give you a working knowledge of what we mean here. So when we have a satellite and we are imaging the surface, with passive sensing, we are recording electromagnetic radiation. What does this mean? We have sunlight, we have reflection, and then we record its reflection. So this is really the principle behind what we do with passive sensing. But of course, there are problems with passive sensing. Again, going back to the analogy of you taking pictures of this, imaging this, imagine that you're a little bit far away, like the satellite is far away. So how far are these satellites? Only 408 miles away, about 750 kilometers. So they're pretty high up there. So the distance is quite high. And then you can have occlusion problems, such as clouds. Clouds might get in the way. So cloud cover is a big problem with this type of imaging, because if you have clouds in the middle, there is going to be dissipation and you're not going to be able to see under those clouds. And another very important concept here is terrain. So how do you do terrain corrections? The reflection is easy. These equations are actually much easier to solve if there is absolutely no elevation change to the world, especially if it was flat. It would have been a very easy to image planet. It'll make our lives much easier. I can see some of you really hoping that that was the case, because it does create a lot of headaches for those of us who process data day in and day out. But we have curvature, and we need to have these terrain corrections. And this is another important part that we have to keep in mind. The terrain correction, we have to take into account what we call the digital elevation model. How is the elevation, the terrain is changing, because it changes the signal that we measure. It changes the travel time of this signal. It impacts how much it's going to be dissipated, diffracted. So this is quite important to understand. And one last thing, another simple point I want to make is Earth observation doesn't only mean satellites. We have many different modalities of Earth observation, and they all have their places. So I want to talk about this a little bit. We have drones. This is an example of maybe a quadcopter, hexacopter, you name it. These are very useful when you need millimeter level data. For example, precision agriculture, if you want to understand how plants are growing over time, if you want to measure their greenness or plant disease, or if you're out in the field doing geological surveys and looking at tiny fractures, you need this type of information. You are not going to be able to capture this from satellites. And we have large area surveys. There are great examples of this. The one that comes to mind is GAO, the Global Aerial Observatory of Arizona State University. This is basically a Dornier plane that has a lot of sensors, satellite-based sensors attached to it. So they do flights just like a regular airplane, and they collect data. But when we compare UAV versus the plane, there's already a resolution difference. And there's also this response time that's very important. For example, if I need to image this area with a drone, I can fly it whenever I want and image it. If I need a satellite image of this conference center right now, well, if the satellite is not passing over this conference center right now, that's just not going to happen. So there's also this concept of being able to get the data when and where we need it. And the last one is satellites. This gives us global data, which is very important to solve these large-scale problems. Of course, there's less frequent revisits, and there is no response time. As I said, we don't get the control. I can basically be capricious about when I need my data. I'll have my data when the satellite is flying over it. So another thing I want to talk about here, and this is really mostly for reference. We are going to be sharing these slides. Mine will be available fully. I'm not going to talk on behalf of Oak Ridge National Lab, but I know that they're going to be coming later at some point. So the World Reference System. So I was talking about how satellites follow a trajectory. One thing we need to know is, okay, for a given location, say Seattle, for Landsat 8 satellites, when is it going to be flying over at this particular location? Well, there is this referencing system. Since we're going to talk about programming in a little bit, if you're thinking about this as a 2D matrix, you might think this as at what time, at which X and Y is the satellite going to measure. So we have this row and path indices. So the path index basically defines in the longitudinal direction where the satellite is going to be, whereas the row defines latitudinally where the satellite is going to be. So this gives us a data frame with which we can collect satellite data and with which we can analyze the data. So understanding row and path is very important, and there's a unified system for it. It's called WRS, or the Worldwide Reference System. So here's a close-up of these. The different colors obviously indicate that the variable is changing. So path is going in this direction and row is going in this direction. So if you need to know what path and row index a specific place on Earth is, you can find it. It's kind of like being able to say, well, Seattle corresponds to this row and this column of this two-dimensional matrix. We know we have this structure for our data set. So today I'm going to talk a little bit about Landsat because I built the hands-on example around Landsat, but the concepts are very interchangeable. But since we're talking about Landsat, I also want to mention that when you look at different data spans, for example, if you need data from the 90s versus 2000s or 2010s, probably the sensors themselves will be different. We are kind of used to this with our phones. When you look at the pictures that you've taken, those Kodak cameras in the 90s, the resolutions are different, the images are different. And we kind of see that with the sensors too. The resolutions change, the type of data that we can collect change. And there is this span of data that's being collected with the Landsat series. So right now, we have Landsat 8, and Landsat 9 is going to be coming online soon, hopefully. But right now, the latest and greatest is Landsat 2013. Landsat 9 is out. I haven't worked with Landsat 9 data yet, but currently we work a lot with Landsat 8 data, which has been in orbit for over a decade now. So this is going to be my only text overloaded slide, but I think it's important. So let's dissect this, because when we do our hands-on section, this is the type of text that we are going to be bombarded with. And this really just kind of looks like Klingon. So let's see what these different denominations mean. You will always, when you get a Landsat image, you will always get this L. So that just means that this is Landsat data. So this L never changes. And in the second position, you will get information about the sensor type. So what kind of, you can think of this as what kind of camera, for example, is being used, what kind of sensor is being used to collect this image. It can be C for OLI TIRS, and I will talk about what these sensors mean in the next slide. O for OLI only, T for TIRS. So I don't need to read this one by one, but the second position is basically the type of sensor. What does this mean? If you need infrared, you probably need specific types of sensors. So you should be looking for those sensor codes. And the other one is the satellite mission number. In the previous slide, I talked about these different generations of Landsat. Do you need Landsat 8 data? Or are you requiring historical data where you need, say, Landsat 4 or Landsat 5? So you can enter that, or you can see that in this mission number. And the L's here, they're generally overlooked, but they are very, very, very important. I can't highlight these L's enough. So processing correction level. One point I made in my initial slides is terrain is important. You have to correct for terrain so that you're looking at a quote unquote correct image. So what we always want to see in this LLL slot is L1TP, terrain and precision. It's precision corrected and there's terrain correction. And also the data provider is confident about this correction because they run correction algorithms. And just like any algorithms, there might be things like overflows, there might be non-convergences, they might have issues when they're processing this. If they don't run into any of those issues and they're confident about the correction, you will get L1TP. This is the highest quality data that you can get. If you get to L1GT, you can think of this as, well, there's terrain correction that's being done, but then there might be some problematic areas to that image. So globally, overall, it's not at the L1TP level, but it is still terrain corrected. L1GS means that terrain correction was attempted, so corrections were attempted for this image, but they were not done. They could not be corrected. That can be due to many issues with the signal itself. But one thing you probably don't want to do is, if you're working on this research project or your company's working on this project, basing a lot of deductions on L1GS data, because the corrections can actually make a big difference. So the highest quality data that you should be looking for is L1TP. And what we see here with P's and R's, these are the path and row. So they change with geographic location. As I said, Seattle has a specific path and row index. So for the same satellite, everything, it just basically gives you the spatial subset. Where is my data coming from? So for different areas, you will get a different coding for this. And the capital year signature is the acquisition year. So when is this data collected, followed by when is this data processed? You might actually see data from the same row, same path, same collection year at different processing years. And generally, if the same data has a different processing timestamp, just a general rule of thumb is its quality is probably higher because it might have been reanalyzed and recorrected to a higher tier. And also, we have the collection categories. RT is real time, which means that you can get satellite data captured over an area of interest in real time, like today. And then we have tier 1 and tier 2 that add some time lag to this data that's being collected. We will see this in our hands-on example, but I just want to give you a reference, kind of like a look back of where to go. And you can find this also in USGS's manual about Landsat. All these Landsat satellites, like any great piece of electronics, they come with handbooks and manuals that you can read if you care to read them. So you can find this information there as well. So we talked a little bit about sensors. So let's talk about these sensors. OLI is Operational Land Imager. So it produces data products at different resolutions. So it has a 15-meter panchromatic image and 30-meter multispectral. So multispectral, Felipe has some great examples of this. He was talking about RGB, how these channels, these RGB channels can have different types of information, like infrared in his example. So this is multispectral, basically collecting data from different segments of the spectrum. So we have this type of image. And global view every 16 years, as you now know, they collect data on a swap. So every 16 years, we can produce this imagery. TRS is thermal infrared. So if you're collecting thermal observations from the surface of the Earth, temperature information, it's at a lower resolution. It's at 100-meter spatial resolution. And again, the SWAT size is the same. Actually, the SWAT size in all of these is the same with the exception of ETM+. And just a small picture here, this is the qubit detector array. So this is a part of the TIRS sensor. This is just to say that all these different projects have very specific sensors that continues to collect data. ETM+, this stands for Enhanced Thematic Mapper. Again, it's a 50-meter panchromatic, 30-meter multispectral. So we have the 30-meter resolution. And also it enhances TIRS in that it gives us 60-meter thermal data. So this is a newer age sensor where we can collect this type of higher resolution thermal information at a smaller swap. One of the sensors that you have seen, sensor types, I'll quickly go back, is TM. So TM is basically succeeded by ETM+. So this is a newer age one. And the last one is the multispectral scanner. So you can see that this is a rectangular box. So it's not square the resolution, the pixels. So this is an 68-meter by 83-meter resolution. And you can get global view 16 to 18 days, depending on the type of data that's being collected. And just to give you an idea, like what does a 30-meter resolution satellite image look like? What is 15-meter? And again, I stole another image from USGS because they explained this in a great way. So when you look at a ballpark, so when you look at a 15-meter, you're really inside the play area, right? 30-meter, you have all the bases covered. And 100-meter, you're looking at the field. So just to give you a sense of the resolution, the highest level that we can collect right now is with the Landsat is 15 meters. So you see that this is still a pretty impressive resolution, given that this data is being collected about 750 kilometers away from this point and globally. So that's all for the quick introduction for Landsat. That's not good. Maybe that was a sign for me to stop talking.
Or keep talking.
Or maybe, yeah. Either. We'll try both. So with this being said, I'm going to jump on to the hands-on section where we will walk through this Colab notebook, just to give you an idea of, well, how can you utilize this data that is publicly made available to us. So you can find a link for it in our webpage. And as I said, if you want to follow this along, all you will need is an AWS account. If you don't have an AWS account, don't worry. I will still talk about when you start an AWS account, how to use it to get to this data. As I promised, the batteries are included in that. The libraries that we will use are here. They are not a part of Google Colab. These are not standard Python packages that Colab ships with. So we will quickly install these. One of them is the PyStack client, and other one is Raster.io. These are very frequently used packages. And as I mentioned, this notebook will be available for your reference anytime you visit the conference webpage. So if this is your first time running this notebook, and if you do want to follow along, you can go ahead and run this in a Colab notebook. It'll install these packages for you. And one thing to note in the Raster.io is it actually has an S3 module. S3 is in an AWS S3 bucket. So here's the great thing. These remotely sensed data products, there are just terabytes and terabytes of data flowing in every single day. So it's really hard to keep it on your drive, and you don't have to. If you need data from a specific location, specific time, you can just make a quick ping to the S3 bucket that has this data set at the time and location you need it, and you can just get it from the cloud to analyze it. So you don't even have to store this data. So for those of you who are following along, this might take a minute or so to install these packages. So let's quickly talk about what's happening here. So Landsat is a USGS product, and they have this in a server. So what we are doing here is basically connecting to the server and getting different types of collections. So when we look at collections, one thing you will see is L2, L3, L1. Yes. Sure. That's a great idea. Better? Can you see in the back? No? Sort of? Let's see. Yeah? Okay, great. Yeah, thank you for that. So we have these different levels. And as I mentioned, these different levels also give us an idea of data quality, right? So this is important to think about. So one thing I'm going to do is, again, for us to not staring at the wheel of death just spinning and spinning, you're going to get a small spatial subset of the data as opposed to getting data globally. And this is also a good moment for probably, unless you're looking at a global problem, if you need data over an area, you can subset this on the server side. What do I mean by this? You have Sentinel-8 data globally available every 16 days. But let's say that you need only data over the convention center for some reason, or Seattle, right? You can only ask the server to give you the data for that location and nothing else. So you're not going to be moving terabytes of data in and out. That already helps quite a bit. So this is one way to do that, where we can define a geometry with the coordinates. You can think of a bounding box where you have minimum latitude, maximum latitude, maximum longitude. So you're basically defining the four corners of that rectangle here. So this is somewhat of a mystery for now. What are these latitudes, longitudes correspond to? And we'll do a little quiz when we look at the images to see if you can determine where in US we're looking at. This is a place in US. But this is a bounding box, basically. These are the bounding latitudes and longitudes for it. So now we're going to make a query. Yes. It's a good question. So for the recording, I'll repeat the question. The question is like, is there any problems with projections and mosaicing when you use something rectangular? Because that's a great point. What we are imaging is not rectangular. So what we are basically using is already mosaic image that's being served. So we are not actually grabbing swaths necessarily that intersect and then mosaic on the fly. We are already working with the data product itself and getting that subset. That's a great question. So after we define this bounding box, again, when you visit this, revisit it, I think this is the part that you will be modifying the most. So how do you make a query? How do you get satellite images? Because this is us asking the server, this is my criteria. I want Landsat imagery that intersects this geometry within this bounding box in this time period. So basically, I want 1 year's worth of data all the way up to our session today on the 17th of June 2024. So this is the time slot I'm looking for. Another great thing here that you can do is you can set a threshold. You can say, well, I don't want any noisy images. I want cloud cover 95%. What that means is in any scene, at most, 5% of the pixels are cloud. The rest doesn't have any cloud cover so that you can actually see the surface. You can be more strict with this. You can try to up this to 100. I don't know if you will get a lot of pixels, but 95 is a good rule of thumb just to get started. Just to ensure that you always get some data. We are going to be looking for level 2 data. So again, this is data that we have some corrections on. So this is my search criteria. And I'm asking the Landsat server to give me data from this time interval within this geometry with all these parameters that I ask it. So when we run this, sure.
Is that 95 there? Is that like an actual query or is that referencing like a produced product that is cloud?
Oh, so this is an attribute of the data set itself. When the data is processed, this is already for that row, for that area, this is already identified. So for that row and path ID, so in that small area that our satellite covers, the processing step done by the data provider already reports what is the % cloud cover. So what we do is in this area, we are only taking in the areas that have at most 5% cloud cover.
You could swap that. You could set that.
Yes, yes. Yeah, you can definitely reduce the tolerance here. But especially with Landsat data, you're just going to start seeing a lot more blobs on your image that just bleed over to all the features that you're trying to capture. So with this criteria over that box that I specified that satisfies all this criteria, I was able to find 105 Landsat scenes. So just to give you an idea of what do these scenes contain, well, they contain some geospatial metadata. So it gives you the type. So we know what the type is, the properties, like what are the bands that are collected, the geometry, the extent, the bounding box that goes with this extent, which USGS collection it's in, etc. So this being one thing I also want to do here is just to show what is inside this assets parameter, which contains data, the satellite data itself. And I would like to direct your attention to these all the way to the QA. So what I highlighted here. So again, Felipe was talking about this, right? Not every image is RGB. That is true. Even though we have blue, green, and red, we have others. We have NIR, so we have near infrared. We have the SWIR bands collected by different sensors. And also we have QAs. So QAs are very important to look at. So this stands for quality assurance. So it tells us whether or not these pixels that we're looking at, is there quality assurance? Is there a lot of noise? Is there a lot of uncertainty? And we can get this information for the data set that we're getting. So with this in mind, I'm just going to start printing some direct links to data in the S3 bucket that satisfies our criteria. You see that we are getting data from the OLI TIRS sensor for 2023. And now you know that this corresponds 24,033 corresponds to row and path index. So where is this data set? Those two combined gives us an actual location. And here is why I put you to the torture of talking about this long overloaded slide. It's the data description, right? So when we look at this, you see that so Landsat data. So this is Landsat 8. Question?
Are all of those nice pieces that are baked into the file names, stored in, machine readable metadata as well, or is it generally necessary to parse that information?
That's a good question. I always go to the file name. I'm unsure. It must reside. I mean, it should be in the metadata, but I always parse it in the file name as I'm reading them. Yeah. So again, coming back to this, so we have Landsat 8 data. It's the row indexes when the data is collected and when the data is processed. So with a lot of data sets, we mostly get 1 or 2 week lag between acquisition and processing. So you see that this data has been processed 5 days. Within 5 days, it was acquired. And we see information such as B4. So this is the 4th band that has NIR information. So these are all the different Landsat scenes that we grab. Yes.
The processing correction level on these is L2SP.
Yes.
Which you didn't talk about that one.
So so this is level 2 data, which means that the terrain corrections are either being done or attempted.
So this is even higher than the L1 TP.
No, this is the 2nd tier, not the 1st tier. So far what we were able to do is and for none of these, you actually don't need an AWS account. So this is just metadata so far. We are just getting information about the data itself. But this is basically as far as you can get without AWS, where you can get the addresses, S3 addresses of where the data lives. And an AWS account helps after this stage where you want to read this in Python. There's a data frame. So for this, I'm going to use Raster.io. This package, Boto3, is again highly recommended. Just like any programming language, there are at least 3-4 packages that do the same thing. And people who develop them will always claim that their package is the right way to do it. I find Boto3 to be useful when you're working with S3 buckets, especially for Landsat data. I highly recommend it. And I'm not involved with people who develop Boto3 at all. So this is my unbiased opinion, if you're wondering. So one thing I'll mention here, and this is really the logistics. Sometimes that's a little cumbersome when you're first getting started doing something like this. When you create an AWS account, you have an access key and a secret access key. So you can think of this as like your username and secret password token. You can get that from the AWS site. The easiest thing to do is to store it in a CSV somewhere and not hard code it onto your notebook. That's always ill-advised. So that you can just read it, because you will need this information to get your credentials. So I have got this information and saved this in the CSV file. And all I'm going to do, and you can use this here, just going to authenticate an AWS session using my credentials. And I'm going to start reading some files. And this function is from a tutorial from Spatial Data Science. There's a GitHub repository on spatial data science, and this is one of those functions. But I think this is very useful to talk about some of the things we can do. So the main function we're going to use is called Rio. So for all of the S3 locations, we're going to be reading it from the cloud, and we're going to be representing this in Python as a data frame. So what are some of the things we can do? One of the things we can do is projections. So Felipe mentioned projections are very important when you're working with geospatial data. So here we are going to be projecting everything to 4326. For those of you who are in GIS, this is the bread and butter projection. This is WGS84 projection. And this is the code for that projection. So whatever projection the data comes in, it's first transformed into this specific single projection. And this is very important to work with the same unified projection for all of the data sets. Of course, when we change the projection, the boundaries of our data set will change, so we have to transform those two so that we can start getting our data projected with the correct, with inside the correct window, because then we use this window from these scenes to only get the data where we need it inside the bounding box we decided. So I'm going to define this function. Another function I'm going to define so that after this we can take a look and see what these will look like. In remote sensing, we work a lot with indices. So sometimes an attribute we're looking for may not be very visible in the red band or the green band or the blue band, but when you combine these three bands to create another band, another index, features might be more visible. So this is exactly the case. NDVI is one of these. This is a greenness index. So if you're working on agriculture, if you're working on plant pathology, forest management, you might probably are working with NDVI data. And this is how it's derived. It's basically this equation is the difference between near infrared and the red band divided by the summation of the two. And this gives us a much clearer picture of the greenness of the scene that we're looking at. So this is an example of an index. So basically, I'm just going to use these functions to start reading the data, calculate this NDVI index, and plot these NDVI indices. So now we are getting this greenness index, and these are all the scenes that conform to the bounding box I created. I guess this is the big question. Where was the bounding box in US? Are we able to see it? I mean, I know a couple of you. St. Louis, exactly. I know. Doesn't help working for St. Louis University. This was a very underwhelming reveal. But yeah, so this is St. Louis. You can see the Mississippi River. You see that a water body's reflections is so much different, especially when you're using a greenness index. You can really see areas where greenness is much higher, like open green spaces. You can see that there's a big disparity here. So this is just a quick example of querying Landsat data, getting this on your computer without having to download data in Python so that you can start analyzing it and calculating an index. So with this being said, we want to take a half an hour break after this. So
I think we might be a bit early, so we can maybe go over a little bit more. I can go over like other types of resources that are available, but first we can probably take a Q&A right now.
Okay, then we can do a quick Q&A if there's any questions about this code. But when we go on our coffee break, which after you cover one more thing.
Break, I believe they're scheduled for 3 p.m. So we are at 2:30 right now.
Okay, we are early. But during the coffee break, what we plan to do is, if you have very specific questions to this code, or if you want to bounce ideas for specific things you might try to do with Landsat, I'll be here, and one of my students, Donovan, will be here, so that we'll be walking around answering your questions if you want to ask them. Yes.
Just gonna propose, if we're ahead of schedule, maybe we can just move on and then we can leave half an hour early.
Yeah, we can keep going out. Sure. There are a few things that I had listed to show more at the end of other resources, like we are showing here one example of data source and libraries. But I can spend a little bit of time now covering other things that you guys can look for, like how do you visualize this data? What are other sources of data that are out there and so on. So that's what we can use this time now.
Yeah. And we are over prepared. So even if we're early, we might not be able to promise leaving early. We do have, I think we have like at least 7 hours of material for this.
Question, so I joined.
Sure.
So this code, I went to the website, I wasn't able to access this one. Oh, I didn't see the link. Is there a?
It's in the schedule.
Okay.
So it's an embedded link in the schedule.
Okay, cool.
Yes. But we'll double check if that's an issue. Yeah.
Sure.
Let's listen.
And second question is, so it seems like when I just Google the Landsat, it's a free database. What's the difference between that and let's say Mapbox or Maxar? How do they, like, if it's free, why do companies buy it?
So for one of the things they have, like for example, Maxar, they might be serving indices derived from the Landsat data. So that's processing. One processing we did is very simple, NDVI, right? But there are a lot more processing you can do to create an actual data product, something more actionable. Like when you look at this data set, you have an idea of do and don't, and that requires a lot of compute power. So that's already secondary data based off of Landsat. And another thing that companies like that do, they have what we call dove satellites. They're much smaller satellites. They orbit at different, basically depending on the mission, they create much higher resolution imagery. For example, Maxar is one of them. Planet Labs is one of them. They do have sub-meter satellite data. They produce that with very special types of satellites. So they charge data premiums for that. There's actually a big asterisk. This is freely available data, but here's the asterisk. USGS, so the US government collects this data. They make it publicly available, which is wonderful. But then this data is served somewhere. And the AWS scheme that's called is requester pays. So when you request this publicly available data, I mean, at some point, this lives in a server somewhere, right? So somebody is paying for something. As long as you don't exceed the limits,
I see.
it's free. But for example, if you're continuously streaming Landsat data in analysis, at some point, you will start paying AWS charges if you go over a limit. Because even though free Landsat data is served as a part of the requester pays schema for payment.
Can I ask one more question?
Of course, yeah.
So I'm familiar with Maxar, we get their data, so when they come at 30, and so they do some enhancement to get it down to 15 meters. What's the best resolution from Landsat that we can get?
So it depends on the bands. We do have 15-meter resolution data as well, but it really depends on the type of sensor that you're looking at. So again, there are a couple of things. We will cover this. I think both of us are going to cover this. When we get to the machine learning aspect after the break, there's a whole family of methods called super resolution methods, where you can take, I mean, this already exists in image corrections. Like you can take a very blurry picture with your phone, but an algorithm can really crispen everything, right? So with satellite data, we have a lot of terrain information. For example, we might have on the ground LiDAR data where that gives us centimeter level terrain information. You might use auxiliary data like surface types for reflectance corrections, etc. We can just take the raw data and use super resolution CNNs to create a much higher resolution version of that data. But at that point, that's a data product, not the originally sensed data.
Yeah, I think that's what Maxar is doing. Thank you, appreciate it. Thanks.
Before I move to the slide deck, you guys have any other questions related to the code here or anything?
One quick question. So in Maxar and the sample, I remember reading in the regulations that you are not allowed to in-paint or modify the images. Is it the case with Landsat?
So in terms of the application, does not work. I'll just make it easier. So I think it's application dependent, but on the legislation side, I'm not quite sure what the restriction with Landsat is. Again, I can talk about my sphere. When you're doing academic research where the data products are publicly available, like there aren't really a lot of restrictions, but that's all I can answer to. Do you know?
Well, I don't have a direct answer to your question, but I think a relevant comment in touching both questions is how things work with the other side of things of like instead of always using this open, somewhat lower resolution in a sense. Okay, I say somewhat lower because when you talk about 10 meters per pixel, sometimes to people like from more like climate domain or someone, they say, oh, this is super high resolution. While doing the type of work like I illustrated at the beginning about building footprint extraction, that you want to look at a very specific structure. If you see an image that the resolution is worse than 70 centimeters per pixel, you'll say that image is bad. So it all depends kind of the application and so on. And there we work a lot with imagery from Maxar. So Portfolio 3 type of data, so to say like a 0.5 meter per pixel. But then you rely on agreements. So it can be agreements maybe from who is sponsoring your research that has something in place with Maxar, or maybe things cascade of some sort of governmental agreements. And that also touches on how you have the coverage for this data in certain areas or not. You can get into some messy situations of like somewhat thankfully, I'm down the pyramid enough that I don't get to see too much of how things work. But you can imagine you have multiple events of interest taking place at the same time. Who gets the highest voice to say, like, task your satellite to look at this place right now versus looking at the other place. So it becomes, again, that trade-off of the availability versus the quality of the data, what you can do or not. So these types of open data can be very relevant, in particular, if you're thinking about covering areas as large as the entire world and somewhat frequently versus if you're relying on sporadic acquisitions that is very high resolution. So.
Yeah, I'm wondering, is this pretty tied to AWS, or do you know if there's like Google Cloud and Azure?
Yeah, so there are many ways to get this data set. So this is what I consider as a native way where the data provider has this agreement with AWS. So you don't find yourself working around somebody else's API they built on top of this. But there are, for example, if you just want to be able to download scenes without writing code, one place I highly recommend, which happens to be my old ex-employer too, but Esri, they have this open system called the Living Atlas. So Landsat imagery, you can just look at times. There's actually, they have a great tool called the Landsat Explorer, which is a web tool. You can search locations like with a click UI on a web page. So you can download scenes that way. Another one is the Google Earth engine. They also have availability on this data set. I'll just talk louder. So Google Earth Engine is another place you can use, and Google Earth Engine's API has specific APIs to get Sentinel data. So that's another place to look at. Any other questions about this notebook? Yes.
What format is the tips? Is it GeoTIFF?
Yes, everything. That's a great question. Everything is GeoTIFF because in addition to the pixel information, the metadata contains things like projections, bounding boxes. So it's all in GeoTIFF format. It's a good question. Any other questions? Great. And if more questions come up, as I said, we're going to have an unstructured Q&A during the coffee break. I'll be happy to answer those questions as they come up.
And the question about the other sources apart from AWS is, thank you, perfect plug for what I want to jump onto right now. It's essentially, it's showing a little bit of the other resources that you have. For example, the Google Earth engine that gives you a lot of ways of downloading the data, processing the data, and they also have some collab notebooks out there that you can play with. So let me jump to those slides here, which I believe are, maybe 1 second just to localize which deck I had this here. I think it might be the very end.
When you're looking, one thing that came to my mind about your question, like one detriment you might have using, like going outside of AWS is like, for example, this happens with the Google Earth engine. This being massive data, and if they're serving it for you, their archive span is generally shorter than what AWS has with AWS. So if you're looking at very historic data, that might be harder and harder to get. Like I have many notebooks that broke now because they are referencing data from like 2010s, etc.
Does that impact cost at all too? Is it like I know you mentioned if you exceed the threshold, data being pulled in, start paying a fee for that compound if using something other than AWS?
I'm not quite sure. I haven't been using Google Earth Engine for a while. But it might. Yeah, I don't know what their data structure is, fee structure is.
Yeah, I haven't either, because again, I work with other types of data mostly, but I would guess it's a pretty high threshold because many people do research using Google Earth Engine to essentially allows you, not only you have a large gallery of data sets there that you have indexed, not that all of these data sets were generated by Google or anything like that, but it essentially gives you a way of searching through those databases. And then you have these Python APIs and so on. And also they have some pretty cool different types of applications of plugging in whether computer vision types of tasks on top of these images and so on. So that's one of the resources that I would encourage as well you guys to play with if you're more curious about. And then there are other resources both around data downloading, processing, and also the coding part. So Orhun has mentioned in the tutorial how the rasterio is one of these libraries very widely used for your loading both your TIFFs, and also you can play, I believe, with the rasterio also with vector data, right? Yeah. So that's one of the things I'm gonna touch a bit more when I mention about the examples of these machine learning tasks, is that when we think mostly, let's say, like those benchmarks for computer vision, you're essentially thinking about your input are rasters or pixels, and your outputs are pixels, like segmentation maps or something like that. When you are dealing with these geospatial domain applications, at the end, people interested in using your predictions, they want to see maps. They want to see things like localizing space and use their tools like what is an Aerotree tool or an Open tool that essentially you load then representations that are polygons. Those are vectors. So you have this extra step of how do you convert from the predictions of pixels to polygons that are like are geolocated and so on. So these types of libraries that are useful for that. Rasterio, one of them. There is another one called GDAL that if anyone has experience, probably we can go like the whole session just talking about GDAL because it can be a pain. Like me, when I 3 years ago started going from like just more general computer vision, started to play with geospatial data, that was my main challenge because it's that kind of library that you have so many things built on top of it. It allows you to do so much stuff, but it has so terrible documentation and lack of like tutorials or anything like that. It's getting better. There are like some wikis or Medium posts and so on that you can find around it. So I mentioned here that if you start to play more this data, you inevitably kind of need to work with GDAL. It allows you to do great things of like this rasterization and loading the data and so on, but can be a bit painful. So just hear this caveat about that. I don't know if you have any other comments about
That's on point, yeah. Generally, the doc on that is interpretation of somebody's interpretation, so.
Yeah. So, and then more related, so in this next part of the talk, right after the part of the talk about after that coffee break, I'll cover a little bit more of like this image classification, segmentation, especially self-supervised learning parts. I'm going to talk quite a bit about what has been going on in this domain, because it's where you start to have more of the unique aspects of the data characteristics of geospatial, how you can leverage that for training better models and so on. And then there are some very cool repositories like the Torch Geo. That is one repository you can go to that also has some very nice getting started kind of sources with Jupyter notebooks, I believe in Colab as well. That goes both from this data loading part and also using some models out there, whether it's for image classification, segmentation, and so on. So binding together this aspect of like this data loading and also conventional PyTorch kind of functions. So you can imagine it's almost like a wrapper, or as they say, it's supposed to be like similar to what you have Torch Vision, where you can get many of those implementation architectures and other things for geospatial data. And then there is another super cool repository that's this satellite image deep learning. This has grown so much over the years. It was like one of these unsung heroes that you see sometimes in Twitter or someone, his name Robin Cole, that he started putting together these things, and then people started to become as a community. So it's sort of a volunteer-based kind of thing that you have many lists of what are the data sources you have, or some of the data sets, labeled data sets for the different types of tasks, or the different types of models with checkpoints available and so on. So this can be very cool if you want to search for like data sets, models, and on and so forth. And another thing, in terms of data resources, we mentioned about Landsat. Some other things to mention is that you have this aspect that I mentioned, how hard it can be to get these high resolution images. But many of those providers like Maxar and Planet and Umbra, they have what they call the open data programs, in particular for data associated with, for example, disasters scenarios, like natural disasters, so when they make data imagery available there, sometimes with some pointers of locations of where the things happen or not. So this can be one interesting way to start playing with this high resolution data. Of course, the availability will be smaller proportionally to what you have like in this global coverage Landsats and so on, but that's a very nice initiative that there is out there. There are other types of index platforms, so to say, or searchable platforms that you can find data. One that I would highly encourage is this one by the IEEE GRSS. I'm going to talk more about that at the end of our tutorial about community overall around geospatial data, remote sensing. But this EOD platform, the Earth Observation Database, is very nice for you to search for by the type of sensor and also search by the type of task, maybe the labels that you're interested in and so on. So that's another very nice search. The stack index as well is so much similar to what you have from the AWS. Just want to keep track of that. So these are other platforms that you can find a lot of data. Same for particularly the NASA missions, you have the Earth Data Search platform. It's like huge, the galleries that you can have a data like Sentinel kind of data or harmonized Landsat and Sentinel, some LiDAR data as well. So there's plenty of data that you can get out there. Sometimes that is hard to find a unified place to go for them, but that's one of the things that in particular the Earth Observation Database is an attempt to try to do that, to try to start having a more community-based way of people, if they want to contribute to that, it's easy to reach out and put a data set there and so on. And then what I have in the other side here, it's around how you can visualize other types of data. So the QGIS platform is one that is particularly useful in terms of open source, free platforms for visualizing this large data, like the TIFF files that can be covering like a very large areas. You can imagine, we are talking about images that can be like easily 30,000 by 30,000 pixels and multiple channels. You're not going to be able to just load that in a Jupyter notebook yourself. So you have these platforms that build upon things like the GDAL that I mentioned, but in a much more friendly way for you to operate. And you can visualize, you can do some transformations there in your data. Both the GeoTIFF type of files that you have for the images, and also vector data. So you can have, you have the OpenStreetMap, which is a pretty cool platform initiative that they call like the free wiki of the world. It's essentially volunteer-based, where people can go there and they can, for example, say that this building here in this location that has been mapped, it's a school, or it's used for industry purposes, or start adding any type of attributes that can be relevant for other people around the world. It can be researchers or other analysts to make use of this information. So you see a lot of inputs in particular showing up for places when you have some events of interest, whether disasters or something, that people more actively start to label things in the OpenStreetMap. So you can think about a very large gallery of even labeled data you can think of, but from a perspective of like noisy labeled data, but stuff that oftentimes is pretty useful to you to get started in some tasks in some areas when you're dealing with geospatial data. And then I also find the GeoPandas library, another pretty cool source for you to play with vector data. For example, we had in the hands-on part of our information about defining your coordinates. You could imagine you can download some open sources you have of maps where you have the delineations of where is each city, like whether St. Louis or Seattle or some other levels of boundaries. And then from that, the GeoPandas allows you to load this sort of what we call shape files, these vector files, and do operations as the name says, like as a data frame, as a pandas thing. So you have a lot of operations that build on top of the pandas data frames, and also offer you ways of visualizing this data, doing spatial queries and joins and merges. And that has a pretty good documentation, I would say. I've been quite enjoying playing with GeoPandas. So that's another thing I would highlight. And there are many other sort of open projects, whether it's like related to constructing databases and manipulating databases for, like, for example, PostGIS and other things under this initiative called the OS Geo. So it's open source projects that is also very relevant research. Another thing that I'll mention already is there are plenty of cool data sets and challenges in this domain that come often in a year basis. some of these challenges have as well, monetary prices, and they're usually touching in topics that are very interesting from the research community. They are kind of open challenges, whether it's more from the application side, like for example, you're talking about flood mapping, or you're talking about finer grain characterization of buildings, or you can think about like how do you do the fusion of different types of data, like the SAR and optical that we talked so much about. So to mention just two, you have the data fusion series of contexts that's being organized for multiple years already by the IEEE GeoSAS image analysis technical committee. And you also have the SpaceNet initiative that is across different institutions, has changed over the years, but you have consistently data providers, people from academia, people like me, like from more the national labs and so on, where we work in different tasks that have range, for instance, at the beginning for building segmentation or road network, or that kind of illustration is shown about data acquired over this location, same location, but different view angles. And things also related to like multi-temporal analysis. So these are some of the things, if you get more curious to play around, you can either use this data because this data remain available, or keep an eye for participating maybe the next few years. So those are some of the things I'm using the time to cover about resources. If you have any questions around that, we can use this next 8 minutes or anything that we talked about so far. Then we're gonna hit 3, we have the coffee break. And then after that, we're gonna hit more about what we call these common machine learning tasks for remote sensing data, and hit quite a bit in the what we have in terms of those foundation models right now for remote sensing data, because not surprisingly to everyone, because most application domains that you have of AI right now, people are developing foundation models, and the definition could be quite loose, but it's very interesting, the types of data sets, the types of self-supervised learning techniques that pop up compared to what you have for the broader computer vision. So that's the seed that I'm planting for after the coffee break. And if you have any questions for this next 5-8 minutes, otherwise you can use the time to just keep walking to the. Go ahead.
Would you say that GeoTIFF is kind of becoming the primary standard for representing all different formats of Earth observation data, or is there one that's recommended as kind of the best?
My answer comes from just my experience that has been with mostly like RGB, near infrared, and so on. That has been always GeoTIFF that I deal with, but I'm gonna defer the question to Aaron that maybe has experience with more.
I was just shaking my head. I mean, GeoTIFF is very widely used. You also have to think about the data. So that raster data, if you're talking about pixels, I don't know why I'm reading over, I don't think this works. We're talking about pixels. That's okay. So that's a good question. GeoTIFF, I think, is very common when you have pixels. In other words, you have centroids and a uniform geometry around those centroids, pixels. But we have a lot of different remote sensing data. For example, when we collect SAR data, that comes in a format that is known as an LAS. So that's basically the SAR format, because instead of just getting pixel data, now we're looking at point scatters. So it really depends on the type of remote representation. Right. So it really depends on the type of data that you're looking at.
But so you're talking for raster imagery, GeoTIFF is.
GeoTIFF, in my opinion, is the most interoperable one. Especially in your open source, I do agree, like the pixels, GeoTIFF is where it's at. There's also a big story about processing these. For example, if we're working with raw data, like there are these legacy platforms that people in different, like for example, if we're working a lot with spectral data, spectral corrections, etc. There is a type called Mr. SID. Does anybody know Mr. SID? Yeah, you know Mr. SID. Yeah, so it really depends on like also what kind of processing you're going to do on that data, because once you go into that format, it unlocks and locks certain types of analysis.
Do they have like their own API? That
yes. But I think for interoperability for pixel data, GeoTIFF for vector data, shape files, is really the main type. So when you basically have irregular geometries like county polygons, so we're looking at shape files. And for point scatters, the LAS type is basically the main
So
one.
I've heard of the shape file. I haven't really used it. That's like, is that a Google standard, the KML, KMZ, or is that different?
So that's an excellent question. I wish I had a slide on this. That's an excellent question. It's actually not a Google standard. Google doesn't set the standard for geospatial. The standard is called OGC. So GeoTIFF shape files, all of these are OGC compliant, and OGC stands for Open Geospatial Consortium. So this is a global consortium that basically defines what open source or open geospatial data formats are. So shapefile is OGC compliant, GeoTIFF, GeoJPEGs, these are all OGC. So if you want to get like a whole list, I will look for OGC compliant data types.
Now, I've also heard of a tool called Shapely. Is that related to shapefile processing?
No, I think Shapely is a Python package for reading vector data. I don't know the history, but I think they named it because shapefiles are the common vector data types in the open source.
Okay. But they're not like directly. They don't like Shapely isn't designed to process shape files.
Well, the most common vector type, if you're not using ArcGIS, is shapefiles. So probably, yeah.
Thank you.
Yeah. There's a question about.
I can speak to Shapely. It's actually the Python front end to Geos, which is the 2D libraries, which are high performant, CPU based, C++ lens. It has almost nothing to do with shapefiles at all. It just lets you do linear geometry operations rapidly without getting messed up.
Thanks.
Thank you.
Thank you.
I'm not sure if it's like really related to this, but say, for example, when you see like I say crop fields from a top view, there are like certain places there are like terraces which like it distorts like a view or like a shape of the field. Do you ever come across this kind of stuff? And then if you do, then how do you remove those terraces from the field to like make the processing smoother, like make your DM more smoother or something?
I think it's talking about the terrain correction that you were talking about.
Right. So there might be a couple of things. So if you're talking about correcting the raw data because of the terrain, so that's a terrain correction like we were discussing in the Landsat data. So that's basically you need to have a DEM, a digital elevation model, and you have to use that model at whatever resolution it comes in to correct the remotely sensed data for terrain. Because when we talk about reflections, obviously the idealized conditions is flat surface reflection, which never happens. So we need to use that in that terrain correction. If you're talking about different curvatures from different parts of the earth being combined into one, is that the question? So that gets at the process of maybe orthomosaicing. Are you going to talk about ortho?
Like what I'm asking about, like I say, for example, you only have a DEM and that's it. You don't have a access to remote sensing imaging. So in case you have only access to the DEM, how do you get rid of those terrain or like terraces specifically? Because those kind of stuff actually distort your whole DEM. Or like if you want to process something for a specific thing, they come in front of you to do so. So like, how do you deal with those particular stuff? Or like, do you use any particular process to get rid of those terrain or like terraces from there?
I'm not quite sure about the workflow. I understand your question. I mean, your question is like, how do you correct the DEM itself right before the process? Maybe Felipe has an answer. I generally resort to the high resolution DEMs coming from NGA. So these are high resolution. Corrections are already done by the NGA. So that's, I think, the gold standard when you look at DEMs. And they also are working on a unified height model as well that you can use if you have like very big disparities in the areas that you're looking at. But other than correcting the DEM itself, that's not the kind of thing I do.
No, unfortunately, me neither. I know that we have some folks working in groups close to mine in the Oak Ridge National Lab that work together with agencies, as Orhun mentioned, to develop those DEMs, but I do not have the expertise on that, unfortunately. Sorry.
Yeah, the question. So coming at some of the stuff from a computer vision background, kind of moving a little more into geospatial. Sometimes it's hard. You get this feeling like you don't know what you don't know, right? I don't know if you guys had any recommendations for like, you know, at least with deep learning, you know, there's a lot of like MOOCs and kind of survey, you know, textbooks and stuff like that for to get started with. Do you guys have any kind of recommendations for any like, you know, online courses or anything like that you found helpful or you find helpful to send out to people?
That's a great question. They're well deserved. Some of the things that I can mention is like these last 3 years, like when I first moved to this domain versus what there is now nowadays, there's more resources now, which is a good thing. Unfortunately, they're somewhat decentralized, which makes it kind of hard to give an answer to that. Like, for example, I believe that the Torch Geo that I mentioned is a good, locating the wrong computer. It's one that is good because it has these examples like a collab things and so on. And they also have, I believe, some videos explaining a few things. Similarly, for this satellite image deep learning, they also have like a blog kind of version that there are some videos explaining few things. But I wish I could point you to one specific website or a book, but I do not have one that I would mention except for these decentralized resources like these ones.
So the short answer is there is one, I mean, so first and foremost, that coming from computer science, right? When I think of Earth observation and computer science, I mean, it's not a fair comparison, right? These are very different things, but computer science, I think, is like very computation and method heavy and much lighter on the data. Like you can get pictures of cats and dogs, video feeds, it just works. It should. Whereas what we work on is very data heavy in that for very different types of data that you get, the methodology set shrinks or expands quite a bit because it's very much mission driven. So that's why it's, as Felipe said, it's really hard to say, like, if you read this, if you go through this, that's it for remote sensing, because people who work on deformations, they generally work on things like SAR. If you're looking at images, then things like Landsat or the Copernicus mission is basically a whole other thing on its own that we didn't even touch today, but does similar things to Landsat. So it really depends on what you want to do. As you might have seen, there's a gallery section to our webpage that is now currently empty. So that's a great feedback. So I will add a link. There is a spatial data science open MOOC. It basically just says Python code snippets data so that you'll learn how to like read shape files. Where do you find remote sensing data? They don't teach AWS a ton. They just give you small geotests for you to download. But to get your hands dirty more with a broader span, we will just add that link as like an outgoing resource. So if you visit our webpage,
End of the week or something.
end of the week, it'll be there. Yeah.
Just to add to security, I'm also a computer science student. I'm also moving to the spatial stuff. So the thing that most helped to me is I'm usually working on soil data. Like thing I'm like, for example, hill slope model. When I heard it, it's like, I don't know what the heck is this. So I go through the paper, see it, and then as your comp science, it's much easier for you to do the coding up. One suggestion is as a comp science, don't look at the QGIS. It's a crap. The best thing is go for the scripting. If you use a GraphQL scripting is the best thing. And again, the documentation is really bad. So you need to figure out how to do it. This is the struggle for a comp science. So best idea is go through the paper, go through the GRAS scripting documentation, QGIS scripting documentation. Those are the best sources for you. If you ask ChatGPT, just ChatGPT is good at too, because literally these sources are online.
So I don't want to disturb the discussion. I think this is good, but just for everybody. So this is, we are taking a pause. It started actually 4 minutes ago. So we are kind of on a break right now. So we're just going to be having this open discussion. So if you don't have questions, you know, you're not going to be missing anything. We'll come in back at 3:30. But yeah, so I think that spatial data science MOOC covers very specific, a lot of Landsat examples. And I think it's also like the abstraction level. If you really don't need to know how projections work, you can take the projection engine of Rasteroid at face value, assume that it works. The same way you assume that NumPy indices are always going to be right when you read an index, right? So it also depends on the abstraction level with which you want to work in.
Maybe one question. You mentioned already that satellite things are not always RGB, and it's interesting. And I have one personal use case that I would like to ask your experience about. Is there some modalities that can help in detecting trees?
Yeah, like for example, Warren was talking about the NDVI. for instance. Like this is widely used to assess like the health status, for example, for vegetation, right? And oftentimes I see, for example, I do a lot of work and so forth, so that are more like geospatial analysts, that they look at the images and help us, for example, labeling data. And sometimes our focus has been more like, for example, build infrastructure, but sometimes you want to separate the infrastructure from trees. For them to be able to see the trees better, they rely sometimes more on the near infrared information than just the RGB. Because it becomes very evident that green kind of things.
So I make note of that, so, as far as I remember, so the list always grows, but for example, in terms of the indices, there are, right now there are 68 commonly remote sensing indices. Based to combine different types of data. There's actually a journal paper just came out about that, so we'll add that in link. So that you can see like basically a whole laundry list of all the indices that you can calculate and what they're used for. It's out there, so yeah, depending on what you're trying to capture.
Oh,
Yeah.
that's great. How can I access the journal paper? Do you remember the name?
I don't.
Maybe.
Yeah, it's all gonna be in the gallery portion of the web page for this tutorial. So if you revisit by at the end of the week, maybe early next week, once we're back, yeah, it'll all be populated at the bottom of the web page for this.
Hey, one thing I was wondering about, you sort of touched on this in your introduction, so, is orthorectification, I'm wondering, I'm actually much more familiar with the SAR side than the optical side. And there, can be a pretty substantial difference, but, in the, that needs to be orthorectified. I'm wondering, how much does that happen with optical when I'm assuming if you're looking roughly down, you're gonna have much less of an issue with that?
So that still has to be done, because when we think about the SWATs, locations along the SWAT are adjacent. Locations across the SWAT aren't, they're actually collected when the satellite is crossing over a different, when you look at them from as a second, it's actually traveling in a different trajectory, so that still needs to be.
Okay, and are the files you're showing being downloaded, those already orthorectified?
Yes.
Okay. Okay, sure, thank you.
I just had a logistical question. This talk is being recorded. Yes, what is the link to that can be available afterwards?
Yeah, so it's all gonna be in gallery, linked to the recordings, it will post.
In a gallery, you said?
Yes.
Is that the CDPR website or is that something you guys are?
So this tutorial that is on the web page that you can read from the CD.
Okay, cool.
Yeah, so when you click onto our tutorial, I think you can watch and stuff, it shows you that's like.
Tutorial, there's,
What's that?
The recording automatically.
Oh, yes, actually, we've been recording this whole time. I should probably pause recording.
the
No,
link
oh well.
with like
Leave
the,
it there.
where there's the schedule and it has the link to this.
So I'll show you what we
Okay.
mean. So. Yeah, so we have this web page, CVPR. Oh, you're not seeing it. It's always awkward. They pointed something, it's not there. Let's see. So this. Okay, so this is the web page for our tutorial.
Okay.
We created it specifically.
Development of Shapely or?
No.
So here, this is already embedded in the CVPR program, but if you want to take a picture,
Yeah,
by all
take a picture
means.
just in case.
Yeah.
And this talk will be put
So
here.
if you scroll all the way down, we have this gallery upcoming section. So everything I mentioned will be posted like at the bottom here.
Perfect. Thank you so much.
It also goes back and forth between like.
And then-
I have a couple questions that might be a little silly for you.
Oh, that's fine. Please go ahead.
So you do a lot.
Research, for MITRE, I work for MITRE Corporation. And a lot of the work is basically a lot of what we've seen so far.
Essentially,
The problem I'm working on is sensor fusion with radar and optical data, and I have a couple of, I guess, just
Geospatial
general
science.
implementation questions that I was hoping maybe I could get.
Yeah, but like now we catch that right, so we have the same time like this, so we wanna be careful. Feel free to make me some sign.
Let's do 15 minutes for me.
We'll see how that goes, but I think that should have more than that. We'll see.
Yeah, that's true. Yeah.
I think that works. There you go. All right, so we gonna resume with our tutorial. Now talking a little bit first about what we're calling here the common machine learning computer vision tasks for EO data. Things such as image classification, semantic segmentation, object detection, and so on. And I will not spend too much time talking about convolutional neural networks or transformers or all these kind of tools that we can say that have been co-opted by the broader computer vision and used sort of in the same way for these problems. I would rather spend more time on the extra strategies that you start to equip those, whether convolutional neural networks or transformers, or your pre-training objectives when we start talking about self-supervised learning and so on, that leverage then the challenges that we have with this type of data and leverage the data characteristics that can make then the quality of your algorithms better. For instance, one of the things that we want to talk about is like the object detection part. When you think about object detection, you're thinking maybe like this frontal view, you have your bounding box with the coordinates, the X and the Y axis, and then you look at things from above. If you have something in the diagonal, your bounding box aligned to the X and the Y axis is going to be terrible. It's going to be a huge bounding box that is not very well attached to your object. So you need to take care of the rotation aware kind of bounding boxes. So that's one example of extra nuance that you need to develop for this type of problems for Earth observation data. Yeah, there you go. What I want to mention, so the classification and semantic segmentation tasks in particular, a good chunk of the methodologies there, the same that you would have from broader computer vision. There are the nuances that you need to prepare your data loader sometimes to have more than 3 bands and so on. And then I want to touch in these additional challenges related, for instance, to the spatial resolution part. That a lot of times it implies we were talking a little bit over the break of doing what we call domain adaptation kind of strategies. That's one of the things that people try to do to address that over the years. The other challenges that you have associated is like how you have more severe imbalances. So what I have illustrated in this figure in the middle from one paper from CZPR a few years ago is how you have this imbalance between the foreground and background objects that can be much more severe than what you have in the usual what we call natural images, regular computer vision data sets. So you can have a much wider area covered by background with very tiny foreground objects of interest, or also significant variation in the sizes and shapes of your objects of interest themselves. Like we think about cars on these images, you can barely see this resolution there. Or then you compare that to airplanes or full warehouses. So you might have objects that can be very significant variation in terms of scale. And then you can have these other variations, like you have the same area with image acquired at different times of the year. The snow cover is going to throw off your models completely if they have not been exposed to that. So these are some challenges that you have on whether you need to collect more data for each of those scenarios or start to developing some tricks for handling with that. Last but not least, I will touch more at the end on that, but this aspect again that your final product deliveries, sometimes they are not your pixels, they are rather your vectors. And the quality of the vectors, then this step of going from pixels to vectors becomes an additional problem. So some of the tricks that I find interesting from this literature, like segmentation type of problems and image classification and so on. They include how you can have, for instance, in the left side, one work called this RVSA. That is essentially you're equipping a transformer that has this, some transformers essentially to increase the efficiency. You have these strategies of doing windows, right? To focus your attention of the multi-head step that you have in your transformer blocks. These windows then, when you look at overhead image, you have again the aspect of the rotation. So there is this additional clever trick that when you're learning the scalars to define your window, you actually add another regression scalar for the rotation, such that you can have windows within this transformer block that are looking at different configurations within your network. For this aspect that I mentioned about the vectorization part, or going from pixels to polygons, two problems that are interesting here is one, looking at the building segmentation kind of problem. If you try to just go and vectorize what your predictions are, you see that if you look at that pinkish left example, you have a lot of jaggish, like little blocks kind of thing, because they're essentially your pixels. So ideally, you would like to have better ways of handling that. And one of the ways that you can have is you can start to have auxiliary losses. So these guys, for example, what they use is what they call this idea of frame field learning. So it's essentially to learn like the orientations of the boundary around your object at each pixel, each region, that will allow you then to do a better job at your vectorization step. Somewhat along these lines, you have another problem that's sort of a classic in mapping the physical environment, that is the road mapping or road network extraction. That one of the big issues you have is discontinuities. You can imagine that maybe you have a tree growing a little bit over the road, and then when you deploy your segmentation model, you're not picking that as part of the road, so you have a disconnection there. When you start to think about route planning, that can become a problem. So you can try to have, for example, other type of loss function that people use here, where it's essentially to learn the orientation between different key points that you have composing your objects. If you're familiar with pose estimation, you might have seen this kind of idea before, that you have key points there. For example, you have the human pose, and then you have this issue that maybe you have occlusion for one key point or another, and having this orientation, like this point is pointing in the direction of this other one, can be helpful then for you to have a next post-processing step that uses this information to reconstruct better your structure of interest. And then going to what I mentioned about the rotated object detection. Some of the tricks that they start to be like when you look at this conventional RCNN types of families, you have the region proposals. You can try to generate proposals that are different rotations. But then you can end up with a ton of proposals that it cascades in being more computationally complex. You need to have more issues with like your maximum suppressions and so on. So what you can start to do instead of is starting to regress offsets or different variations for your bounding boxes. One illustration is this oriented RCNN, whereas essentially the idea that you have, you can imagine that you have at first your regular region proposal kind of block that will suggest coordinates of bounding boxes, horizontal bounding boxes that look suitable for evaluation, maybe find an object there. But then in addition to just like these X and Y's of your rectangle, you learn certain deviations as an extra regression parameter of how much you should have of a rotation, or maybe or how much you should have of an offset that allows you to compute an angle for this bounding box. So these are very interesting tricks, I would call, that they work pretty well then to enable how do you go from conventional computer vision approaches and make them work much better for object detection kind of problems. And this is very relevant when you think, for example, if you're trying to do object tracking. I mean, like many of the tools that you're going to try to do for that is like to extract the features from your object of one frame and then compare the next one. If you have a poorly attached bounding box, you have a lot of surrounding noise background that's going to give you pretty bad features. So when you think about this kind of cascading issues, it's very important that you do better with this sort of nuances of your data. Another problem that I feel like it doesn't show up as much in the broader computer vision is change detection. Looking from the perspective, for example, of disaster response, I think is one very good example from an application perspective. But you have a lot of data sets. I mentioned you just one here that's a classic, the XView 2, that has images from different types of natural disasters, like floods and earthquakes and volcanoes and so on. And essentially your problem consists of, you have usually an input that gives you a pre and a post event images, and you're trying to estimate the levels of damage to you. At some point, this is gonna come back. Meanwhile, I talk louder. So your task then consists in estimating these damage levels, whether it's to build infrastructure or maybe changing the land, it can vary. And I say usually you have pre and post event images because that can become a problem when you're looking at from an application perspective. An event happened today, and then I get some images maybe tomorrow or so for the post event. And heck, I don't have pre-event image in my gallery. I cannot do anything about it. So there's many works that you have seen that the results are better if you have this pre and post event imagery available. But developing models that only look at post will be like a sort of holy grail approach too. So but they tend to underperform quite a bit. And overall, for these change detection problems, you can have many variations of whether you're using convolutional neural networks or transformers and so on. But the structure, I would say, of your architecture looks similar under this idea of Siamese models. So you can have here different variations. There are two very nice papers that are 4 or 5 years ago, but still remains pretty up to date in these core ideas. That you could imagine that you're just trying to have a comparison of like a individual estimates of your land cover or your building maps. Like you first look at a separate model for pre-event, then you look for a separate model for the post-event, and then you compare difference of the outputs. That's the most sort of naive approach that's not going to work as well. You can think of a strategy B that you're essentially just tasking a single model trying to do the change detection directly. Or you can start to have those Siamese structures that start to look at more your difference in your features being extracted. So imagine that you're looking at either land cover changes or building footprint changes. You can imagine that you will have one model trained for this task for a single image. You can deploy this model for both the pre and post event image. And then you can start to have another module like a decoder head that looks at these different features and is tasked just to learn then these damage levels by looking at these intermediate features. So that's essentially what we're showing here in these strategies in the left. And then extra tweaks that you can compare is whether you're concatenating these intermediate features or you're doing the difference between them. There's been some results showing that the difference is better, but sometimes it can vary a bit, so there isn't really a consensus. But overall, it's minor differences for a methodology that works pretty well in practice for you to enable this kind of change detection approaches. Another thing I want to hit about this common machine learning tasks, there are a lot of data sets out there. So we have covered between before the break about some of the places where you can find those data sets. There's this very nice paper from 2023 from Michael Schmidt and some others researchers discussing the data sets for deep learning Earth observation that they give you. They review over 400 papers. They have supplementary material, the full list of them. They categorize in these categories. You can see that prevails a lot these 4 problems that I mentioned about image classification, object detection, semantic segmentation. Then you have also problems like change detection, super resolution problem, and so on. And the thing then is that you need to keep in mind that there are some biases in this data, as any data, unfortunately. And the biases can be here in different ways. One is that you have much more for satellite than aerial and drone and multiple. It brings back the topic that is worth a reminder that Orhon made, that Earth observations is not just satellite, but there is this bias overall in the data collections as well. Similarly, for this type of sensors that you use, most of them end up being RGB. And the availability of collection of multiple times, it's rare to have data sets that have a multiple times, but it can be very useful. We pause recording. I did resume. You go back to this. And you also have geographic diversity, geographic biases in the sense that you can imagine that stakeholders or the companies operating these data sets, they're located in more developed places, and some events of interest tend to happen more in some other place, in some specific places, so you can have underrepresentation of coverage in certain areas. I mentioned about this before the break, how the Earth observation database can be one good repository for you to search for these labeled data sets, and also some according to sensor type. Just taking a break because I saw people taking some pictures. And the other aspect of Earth observation data that can be challenge, but can be potential for doing great things, there's a ton of volume out there and already archives, and a ton of volume in increasing levels being collected. You can think about hundreds of terabytes of data. And you can deal like with images that can be super big as a single file itself. Like when you mention about the high resolution images that we deal with often, you're talking about images that are 30,000 pixels by 30,000 pixels and can have 4 or more channels. So that requires these extra tools of how do you visualize them, how do you process them. But all in all, that's when you start to think about self-supervised learning kind of practices, where we see now being enabled pre-training for foundation models. There's great potential for that here. Here's just another illustration for just the NASA Science Data Archive. What is the projection that we're going to see as the new missions are added over the next years? We're going to be having a lot of petabytes that can be used for developing models and applications. So with that, I want to start talking about this idea of foundation models or Earth observation. No surprise that this has been like a very active topic now, whether it's in computer vision conferences or remote sensing journals and so on. Because you have these challenges of many of these models that we have for the different applications, they are task specific. You have one model for this task, one model for this other task, and you're still dealing oftentimes with the same type of data. So ideally, you should be able to be leveraged at least part of this model instead of retraining everything from scratch again. Developing models for each task also requires a lot of labeled data. And labeled data can be pretty hard with these very large images and objects that are super tiny. So it's a very challenging effort to label this type of data. So I believe probably most of you are familiar with the idea of foundation models. If not, this concept that you have pre-training of models using self-supervised learning. So you're not requiring labels, using very vast galleries of data, with the idea that this gives you like backbones or encoders or representations that you can then use to more easily adapt to a wide variety of downstream tasks. You can imagine for the type of tests we're talking about, you have a model that is pre-trained, and then you can have different decoder heads more easily adapted for whether it's building footprint mapping, land cover classification, change analysis, object detection, and so on. And then ideally, what you would like to have is not only these different tasks, but also this aspect of different modalities, being able to reason across optical data, across SAR, across LADER, and so on. That is the dream, so to say, when we think about foundation models for Earth observation. So there has been a growing list. Here's just a few. It's a difficult attempt to list all of the things that have been developed over the years. And I'm going to cover a few of them that I've considered particularly interesting in terms of the different strategies that they are using. So this is a slide from Professor Hamid Ali Mohammad from Clark University that has been doing a lot of work on this as well. And we've been working together. He provided this list for us to build upon. There we go. So when we look at the self-supervised learning strategies across computer vision, I think it's fair to say that these 4 main types of, or better saying, these pre-training tasks used for general computer vision, because supervised learning, of course, goes against the idea of self-supervised. But the pre-training idea, you can have either supervised learning for different tasks, or you can have contrastive learning, whether it's with just images and so on, augmentation, or contrastive learning with like language and text, language and images, or the idea of like masked autoencoders, that you have the masked image modeling as a pre-training task. For Earth observation, you see analogous things popping up. You have big data sets being put out of there for self-supervised learning with over large areas. And for supervised learning with multiple labels for different tasks over large areas. You have tasks such as doing similar how you can do text and image. You can think about doing location and image. That's one work I'm going to talk about. And the contrastive learning, the image modeling parts. And when we look at this table that I showed you in the slide before, there's a lot of works being doing, particularly with masked modeling. So, and then a few of them also using contrastive learning. Some recently ones combining these things together. And I'm gonna touch across a few of them that I find of particular interest because of the different nuances of what they are leveraging. The first one is the contrastive learning itself. That is super cool in the remote sensing Earth observation data, that you don't need to rely on synthetic augmentations only. Like when you think about seeing the more conventional types of contrastive learning for computer vision, you do like some blurring, or you do some rotation and flipping or colorization and so on and so forth. For Earth observation data, you actually have data most of the times geolocated, timestamps, and other characteristics there in your metadata, that you can form pairs of data over different timestamps, different sensors, different view angles, all over the same location. So you have this sort of natural augmentation that you can use for contrastive learning and learn rich features out of it. So you have data sets like the functional map of the world. And then you have one of the first works doing this sort of contrastive learning for Earth observation data. That the additional trick that they put in place as well, it's not only that they do the contrastive learning over the image acquired over different timestamps, but also this idea of predicting the location of that image, because they use essentially images from, I think was from Wikipedia that they use in that paper, that you have like the longitude and latitude of where the image was acquired. So you can have an additional type of pre-training task that you can use for pre-training your model. And you can have different variations of what kind of invariants or constraints you want to impose. If you want to do like seasonality being like you want to construct such that the representation across different seasons, they should be similar or they should be different, or what kind of variations you want to have in place. It's another way that you can get creative here. Another very cool work is the set clip, like folks probably plenty of the folks there today at the Earth Vision workshop taking place right now. It is very interesting is that the idea is the same intuition of what you had for clip for doing this contrastive learning between text captions for an image and learning this multimodality in this way. You can do the same for having a location encoder instead. So the geo-coordinates of your image and paired with your actual image. And from that, start to learning embedded representations characteristic of a certain location. So you can think about pretty interesting tasks that you can enable with them. I think this visualization that they have in their paper is pretty cool, how you can look at the embedded space and do like a TSNE type of analysis and see how you start to see some proximities, for example, of certain types of climate zones or biomes being closer together in this embedded space versus in other regions. So you have a way of enriching your purely image representation of the actual knowledge that you get from the location where that image is. And I'll touch a bit on that again when we talk about generative AI for this type of data. It will be like a 5 minutes. I'll just give you some examples of cool stuff being done on that. For masked modeling, there have been plenty of works doing that, whether it's for just RGB images or, for example, how the NASA IBM foundation model called PreTV, that they have been approached this for multiple bands. So they have this data set called the Harmonized Landsat Sentinel-2 that you end up having 6 bands. And then you can play with different variations of how many bands you're using. And what they did is to then essentially expand your regular VIT architecture to be like 3D. So you have 3D patch embeddings, you have 3D position encodings, and then you pursue this kind of masked modeling that in their case demonstrated across downstream tasks that included cloud imputation, cloud gap imputation. So it's essentially, we showed a bunch of examples how you have cloud coverage becoming an issue. You can imagine you have maybe acquisition over multiple timestamps, and you can try to infill that area covered by cloud. Things such as crop segmentation or flood mapping, wildfire mapping, that are very suitable tasks for this kind of image resolution that we have on Sentinel-2 and Landsat. And then there are some extra tricks that you can think about when you do masked image modeling for this type of data, that you can try to think of, how do I play when I have acquisitions over multiple timestamps or different bands? Do I mask everything, that single patch, that location across all of them? Or do I maybe mask some randomly, independently random for one timestamp, and then independently randomly for other timestamp, and then a similar way for the different bands? And then for example, the SAT MAE paper, SAT Masked Encoder paper, shown that they saw some improvements in the model quality if you do this kind of independent masking instead of the patch across all your bands and all temporal acquisitions being always masked. So that's one of the flexibilities you have with this kind of data we have here. The part of like how do you embed in your representations information about, for example, the time of acquisition. So in the same way that you have this position encoders in your transformer modules to denote what is the position of your token, of your patch, when you do the split of the image into patches, you have this position encoding with like a sinusoidal function and so on. You can encode other informations in analogous ways. For example, the time of the month of the year that the image was collected, or which band is associated with that token. Another very interesting one that I mentioned a little bit over the break is this aspect of like how you can deal with this difference in resolution. So the difference is that you have 1 pixel meaning half a meter in one imagery or meaning 10 meters in the other. So the Scale MAE paper, what they do is again playing with this positional encoding, but then infusing that information like what is the resolution of your pixel. And with that, you start to have more robustness, and that allows you to have models that perform better with these variations across spatial resolution. From the supervised pre-training part, there's a recent paper, was actually in CVPR last year, that was called the SATLAS pre-train. It's a pretty big data set with Sentinel-2 in NAPE images. So high res, in a sense, and lower res images. And that's accompanied by a lot of different types of labels. You have labels according to the different, for example, you have storage tanks, or you have power plants, or you have maybe some attributions about the type of structure that you have there, what is the usage of it, or information about the land itself, or some other types of features that essentially allow you to formulate different types of tasks. So you can imagine a pre-training where you have a single encoding module, but different decoder heads for each of those tasks, under this assumption that that's gonna lead you to learning richer internal representations that later on you can replace some of these decoder heads to enable other fine-tuning strategies. And then we go back to also the conversation about multimodality, right? Again, multimodality doesn't necessarily mean image and text. It can mean things like how you handle the different resolutions. You can handle like the passive sensor versus the SARs, and also the different view angles and so on and so forth. Because ideally what you would like to have is this type of model that you would be able to consume data from different data modalities, maybe just a few of them available at hand, but in the end of the day, you would be able to enable all these downstream tasks using whatever combination of data you have available at hand. Because you know that intrinsically you have all this data geolocated, and there is information that you can try to bind and learn shared representations for these things. And then here for the self-supervised learning with multimodal data, you can have strategies that are very analogous to what you had before, like just a simple pairing of patches of the different sensor types that you know are covering the same location, the contrastive learning on top of that. You can try to do some combinations of things. Like you can try to think about like how the Omni set does, for instance. that you have pre-training of modality-specific encoders using a masked modeling kind of strategy. And at the same time, then you have a modality fusion module that learns a joint representation by doing a contrastive learning then across the representations coming from different encoding modules. And another work then, for example, how the Presto work does, you can start to think again of these different type of permutation that you can do in the type of masking that you can do, whether you do like for each pixel alone, or you do across a whole band, or different timestamps, or the different sensors. So you can get creative then with these different permutations of the masking that you can do, and whether you're patching the representation or just playing with each pixel individually. Another work that is very interesting to look at is the climax work that was done, was published in ICML last year. So that's more on climate data, like temperature and many other features. I find interesting mentioning here because these strategies, they're still useful in a similar way, and the challenges are similar in the sense that you have variations in the spatial resolution of your data, you have different types of channels with different types of modalities of your data. So essentially what they have in place here is kind of small to see, but is again this sort of strategy of first modality specific encodings, in that sense, the modality specific tokenization that they do, and then start to leverage this idea of cross-attention mechanisms to enable this mix of your features coming from the different modalities, such that you aggregate these variables, these tokens together, and then you have after that regular encoder transformer, so to say, to learn this shared representation across the different modalities. The USAT is also a similar way. Essentially, the trick that they do here that's very interesting is having this one, the idea that if you're dealing with data with different resolutions, you can try to think about doing more patches for the high resolution ones and fewer patches for the lower resolution ones, such that they're kind of covering the same area each overall. And then you have additional embeddings that tells you what is the band, or is the red, the green, the blue, the near infrared, and so on, such that you can have the separate tokenization first, but then you have like a pooling mechanism that you create a single representation for your patch that then leverages the information across these bands. And finally, another work that I got to it a few months ago or weeks ago through Archive. And then I was glad to see that it's actually part of the conference this year. I think on Friday they're going to be presenting. That is the Sky Sense. There is a lot here going on in the sense of using contrastive learning across the different modalities that they have. The aspect that they have different encoders for different like low res, high res, and SAR imagery. But the one thing that I found very interesting is that sort of along the lines of what I mentioned about the SAT clip, of learning this type of geolocated representation. The way that they do it here is that they do a clustering mechanism in your embedded space that learns different prototypes for each location that you have in the world. Like we split the world in a grid. I think they did like 4,096 regions. And you do this clustering in the feature space for each of these regions, and that gives you a prototype that for each of those locations that they show in the downstream tasks that enable better representation learning for downstream tasks afterwards. Now, the one thing that's worth highlighting is that I mentioned how you have many of these strategies similar to what you see in the broader computer vision being used here, being effective. But there is the aspect of computing availability and resources availability and where we are in terms of model scaling. So this is one of the things that we are playing now at Oak Ridge, I can tell, because we have the supercomputer, the other frontier supercomputer that has, I believe, around 6,000 nodes each with 8 GPUs, so you can do plenty of cool stuff there. But this availability of large high-performance computing resources like in-house on most of these foundation models being done for whether language or computer vision, has been taking place. It's not really the case for most of the research in Earth observation. It's mostly conducted by like whether or smaller companies or mostly academia or national labs and so on. So it's still this step of doing analysis of model scaling. It's something still to take place. There has been more progress now pushing a little bit more to closer to 1 billion parameters in these VITs or variations. But when we look at the broader computer vision, we have things about the 20s and probably more billion of parameters. And when you look at language models, it's even further, that you're talking about hundreds of billions. And that's, you need to be careful, like that you don't want to burn resources just for the sake of it. But it has been shown that the scaling part enables quite a lot of improvements in terms of your downstream capabilities and also this sort of emergent abilities, right? Things that you cannot extrapolate from model like smaller models, but rather you just find out that they show up once you scale to a certain level. Things such as how you see language models being able to do translation or doing like those calculations and so on. And here is just a quick, messy overview that I put in place in terms of some large data sets that I consider relevant for pre-training. So you have data sets for more like optical imagery, such as the function mapping of the world. It has about 300,000 samples. You have the Million A data set, has about 1 million images with land cover labels. And then you have, I mentioned about the satellite speed train that has many of labels across different tasks. You do have as well some more multimodal pre-training data sets. A lot of them are with Sentinel-1 and 2, because it's essentially you have one of the easiest pathways to start dealing with optical and SAR data covering similar locations from this pair of the constellation. And the big EarthNet as well, both its original version, also the multimodal one, pairing again Sentinel-2 and 1, you can do a lot of things with them. And then things are somewhat all over the place in terms of evaluation. So there is a consistency in the sense that tasks that matter are tasks like image classification, semantic segmentation, and so on. And here I say tasks that matter for more like this kind of optical data, satellite data kind of thing. That it's what a vast majority of the works do. But when you start to think about multiple modalities and other types of imagery that are not necessarily optical, there are other types of tasks that can be relevant, whether it's like assessing some vegetation indexes or other types of parameters. So there has been some more works now trying to push for more standardization in the types of tests that you should be looking at and the adaptation criteria. Like I mentioned, the GeoBench paper is a very interesting one to take a look at in that regard, and how they are mentioning construction of data sets, these aspects of licensing, what should be your criteria for whether you're doing a fine tuning with maybe some limited budget to make it more even. And these aspects that both in the construction for training data sets and also for evaluation, the different kind of things you want to consider. But again, I point to this paper about the data sets for deep learning observation. There are no data, more data, that they talk about how you want to data sets covering different seasonalities, different types of data, different types of downstream tasks, and so on. To give one example of what we've been trying to do for creating these pre-training data sets, is this aspect that you can leverage what we call this sort of ancillary informations. You have data sets that give you what are the climate zones. You have data sets that give you what is the population density in certain locations. What are the biomes? So all of this can be relevant and useful for you to create data sets that are more diverse in capturing different types of overall appearances or scenarios like urban and rural and so on. So that's essentially to keep as the message of don't look only at images. When you're talking about geospatial data, there's plenty of other auxiliary data sets that can give you very relevant information that you should be looking for. And then finally, I want to touch a little bit, the next 5 minutes or so, is some progress that has been taking place in the idea of generative AI for Earth observation data. There are things that have been ready or happening for years, particularly using GANs at the beginning, things such as how can you try to synthesize realistic, for instance, satellite imagery from land cover maps as your conditioning inputs. And more recently doing that as well using diffusion models. But a conversation that most often comes when I go talking with people in this geospatial domain, GIS and so on, is this concern about the deep fakes, right? You can think about deep fakes in particular under 3 types of characterization here. There are 3 categories. One is the idea of scene synthesis, like when you can have, for example, you condition on a certain caption that telling what you want to have in the scene, or maybe you can actually condition also in their geospatial location. And you can have other types of alterations, things such as you have a certain layout that you want to create, an image that looks realistic according to it. And then you can have a pairing of the layout with things such as whether the city has been flooded or is after an earthquake and so on. Or you can think about other types of manipulation, like maybe you want this original upper left image to actually have a green area around it instead of just a built environment, or you want to split that big building into 3. So this is actually another work that right now has been presenting, I believe, at the workshop, the Earth Vision workshop by Siri Kumar, Nathan Jacobs, and others. It's a very interesting work that essentially what they are doing is using this aspect of diffusion models and also the set clip that I mentioned before. So the set clip offers you a way of having an embedded space that encodes information about your geolocation. And then you can have a pre-trained diffusion model, like what you have here, this yellow block here, that you can try to further condition it in an image that you didn't see before under this aspect. There's a strategy that's called a control net. Or if you're not familiar, the overall intuition is you have a pre-trained model, like this yellow block. Imagine you replicate this block. You keep one version of this block frozen, and that other version of the block, you're actually fine-tuning for your new data type. And then you pass the features of this new block into the frozen one, and that starts to have guidance for your synthesis to consider this additional conditioning modality. So essentially, that's how they do this idea of conditioning on the location coming from set clip, and also the conditioning coming from this sort of vector maps that you can have. So essentially, how you can try to synthesize images, conditioning text, and this spatial layout. The other interesting work is called diffusion set. That is, I found it particularly interesting that in addition to the strategy of the conditioning is how they embed other types of metadata information. So I mentioned about how some works like the scale MAE does this positioning coding that becomes aware of your spatial resolution. So you have an additional type of information coming from each token that express what is spatial resolution. And here they go beyond that and do like for the geolocation, they do that for the cloud cover, they do that for the time of the year and other types of metadata that you consider relevant for the synthesis of an image. So that's I find it a pretty interesting way of trying to aggregate this information to condition, not images just like what you have in broader computer vision, but also absorb this sort of metadata and criteria that you know is relevant for this type of data that we deal with. We could spend a lot of time talking about this, but just to highlight some of the potential usages and risks associated to that is like, you have many of these work showed up with the motivation of things such as like, you can remove cloud cover. Just go ahead.
About the are most of those methods generate like RGBs, or are there generated models that will generate like SAR or?
It's a very good question. These works that I mentioned, they are tackling more the RGB, and unfortunately, how most of the things unfold is we have more RGB works. But it tends to be that once you have for the RGB, you start to have the further developments. Okay, let's try SAR, let's try the other near infrared and so on. So the ones that I'm aware, they have been mostly RGB. There was before this other one that was using GANs at the time that they did play with SAR. If I remember correctly, the quality for SAR was a little bit worse. Yeah, so the short answer, yes, most of them have been RGB, but I would envision soon you have the natural development that started to play more. And so just mention a few of the things to keep in mind about that. Like, so there's this potential usages for like cloud cover removal or doing super resolution in better ways, or creating synthetic label data sets. Like if you have, it's one of the challenges, like if you think in a conventional way of creating a data set, like for land cover or other types of features, you have the image and then you manually annotate what you have the image. If you can flip things around, that you have a conditioning semantic layout and you condition it, you synthesize an image that obeys it, you already have what is the label associated to that you can do training of models around that. But that can be pretty problematic with like some of the concerns that people have is like how you can imagine that parties trying to synthesize some images, simulating some changes to infrastructure or other types of events, dump that into social media and start to claim a few things. Or even further, when we think about how we scrape data for pre-training models, you can imagine like at extreme that you could try to intentionally make big public data sets out there, or try to poison some volunteer-based data sets with some adulterations that maybe are not very evident, and that can cascade in your pre-training models that can be very problematic. So this overall aspect, when you generate your data, you having the development of good practices of like how do you make watermarks and so on, and documentation, how this data is coming from, like you're thinking about a super resolution kind of things. You need to know where is the methodology being used there to see what actually can use for a downstream test or not. And leveraging the nuances of the data, like how I mentioned, there's this creative ways of at least incorporating metadata and so on. Those are important things to consider. With that, I am done with this part of the covering the self-supervised learning and so on. You can take maybe one or two questions before we jump into the other part of the talk.
Beautifully done. Thank you so much. Such a
Thank
good
you.
review. I don't have a question. It's a comment, and you can maybe elaborate on it. I work in private sector. So, you know, like we have to always use non-commercial, commercial ones. And with this field, it's a little bit challenging. So for example, when you work in the open field of like regular images, the transferability of the models to this field is very challenging. And then we have the problem of like cleared data and uncleared data. So there is lots of review and work being done that is not being accessible. And then on the top of that one, some of the models like Street Clip and building on the top of it like Pigeon and Spade, for example, by NVIDIA, it's all non-commercial use. So anything we cannot build on the top of them because of that one, unfortunately.
I can imagine how challenging it must be. Like I work more in we're sort of in between, could say, between what is academia and what is private sector as a national lab. We're doing applied science, but we are doing non-profit, and we have access a few times like data, for example, the high resolution ones. But then whether you can publish this data becomes a problem, and also what you can use for training this data can become a problem, right? Like I mentioned how it would be ideal for this research of enabling the reasoning across the different modalities, because if you have a lot of gallery of pre-training and low image, low resolution one, that can hopefully enable you to need less data, label data for the high resolution ones. So that's one active field of research that everyone thinks that would be so great to have that. I think it's good that we're finally moving this direction, more self-supervised learning to enable that. But I don't have, fortunately, a solution for that yet. But what I can tell, I guess, is that people are aware, trying to work on that. So
and like sometimes like Spade by NVIDIA is for synthetic data generation. It's a powerful, beautiful model, but it's for non-commercial. So for example, if you want to do a downstream task like semantic segmentation or something like that, you cannot.
Yeah, that would be definitely an interesting thing to discuss more. Like this whole licensing aspects can be very problematic. It's one of the things that we're not covering here, but overall it becomes a huge problem.
Thank you again.
I'm just gonna chime in. One thing you didn't mention was the ontology, like some sort of a standardized ontology for geospatial representations, which I think
you're gonna touch a bit on that, right?
Okay, yeah.
It's the next part right now. Thank you for the plug. And then you can feel free to chime in further as well. Like, all right. I'll pass the mic now.
Would it be possible to have a copy of your presentation?
I'm sorry?
will a copy of your presentation be available?
Just could you repeat what you mentioned?
The question was a copy
Yeah.
would be available. So for myself, yes. And I think,
Yeah, from my end of some of the slides, as a national lab, of course, I'm not showing any classified information here or anything. It's just that you have separate rounds of approvals, one for presenting, another one like for putting out there the copy for anyone to download and stuff. So there might be a little bit of a delay from my end, a few slides just because of that. But the likelihood that I would not put slides is low. I am expecting to put there soon. So all of them, all the materials, they're gonna be at the website and the gallery part there. It's just that some things might take a little bit longer.
yeah, and that's a good reminder. So all the materials that we're gonna provide after this, either supplements or goes beyond what we discussed, is gonna be on our webpage for this tutorial at the very bottom section. So Fibo was right. Your question was actually a great plug, a great segue into what we're going to talk about. So I work a lot on what is known as spatially explicit machine learning. And this is not the kind of machine learning task that is often discussed necessarily at CVPR or NeurIPS, because this isn't necessarily just neural networks. So how do we represent spatial information? How do we represent things like proximity, moving along the same direction, being in the same region? So how do we represent spatial information, like neighborhoods, for example, explicitly at the algorithm level, rather than just trying to learn it after the fact with a neural network? Neural networks are great with learning, but we can represent spatial relationships. We can create, for example, spatial clusters, or we can make spatial predictions. Given set of accidents happening, where is the next accident going to happen, or where is going to be the next hotspot of accidents? Spatial prediction or spatial clustering. Where are going to be the next? What are the next climate regions going to look like? So these are inherently spatial problems, and we can create a spatial representation for more succinct and parsimonious a learning problem. So this is what I will talk about, and this is something that I actively work on in my lab. Since we've seen great examples of supervised learning, semi-supervised learning by Felipe already, I thought it would be appropriate for him to talk about unsupervised learning. So I'm going to focus on unsupervised learning, in particular, spatially explicit unsupervised learning. So as far as I can tell, everybody has some background and definitely a lot of interest in machine learning. So in that pursuit, you might have seen something similar to this, even though it's not in this graphical format. This is something I created. This is from Mitchell's artificial intelligence book. I think that's one of the foundational books when you study computer science and specialize in artificial intelligence, where his point is there is this experience, there is this thing we want to learn. Where are the clusters? Or what is the value of this variable we're trying to predict? Or where are the bodies that we're trying to extract from an image? Where are the artifacts? There's some feature engineering. You can think of this as rearranging your bands, calculating indices, auto rectification. So basically getting your data ready. And then there's some learning process that's being done. And then there is some interpretation of this. And of course, this counters the other way of doing it, which is just using human interpretation and knowledge bases. So creating these ontologies, and especially in spatial decision-making, this was really the field to be in back in the 70s, where if you had an environmental problem, there was a huge repository of next things to check, next things to do. As a matter of fact, people who created the term machine learning back in 1956 at this small workshop in Dartmouth, they were working explicitly on these types of ontologies. But of course, how do we kind of marry these two worlds, incorporate information about what we already know, but still do this in a more unbiased, automated way? So then we talk about spatial representations. How can we take what we know about spatial relationships, represent this in a numerical way, so that we can use some of the existing methods that Felipe discussed? So how can we marry these two worlds? For spatial problems, we can do this with spatially explicit machine learning. I will put this paper, I like the title because it's a pun and I like puns. It's a paper called Is Spatial Special by Michael Goodchild. He's a professor of geography at UC Santa Barbara. He makes a big discussion about how spatial data is special. in that it requires this specific numerical representation. So after we talk about this learning problem, unsupervised learning, just a quick breather. So reminder, we are talking about clustering. So we don't really have samples to learn things from. So we don't really have this predetermined example of what the answer should be like. We don't know the answer. So we need to partition the data somehow without seeing any examples. So we have to describe the data somehow. Rather than in supervised learning, we need to create a function approximation. And in the spatial sciences domain, spatial clustering. So if you look at different journal papers in this problem, the problem is called regionalization, defining spatially contiguous clusters of your data. Think about climate zones. Think about your plant hardiness zones if you have a green thumb. Those never have little islands in them. They are not pixelated. These are contiguous regions. So this is what we expect. So how can we impose contiguity? This is the regionalization problem. And this is what I will talk about as a part of my active ongoing research. So one way of doing that, kind of like your question with ontology, is a graph-based representation. And graphs are a very natural way to represent spatial data and spatial relationships. As a matter of fact, graphs are also very widely used in neural networks. We have graph neural networks for spatial problems. They are on an uptick. So I want to quickly talk about what is a spatial representation. What is a spatial graph representation? What does it mean? So in every graph, we have some vertices. And if there is some relationship between vertices, they can be connected with these edges. So this is basically the simplest way of thinking about a graph. And of course, we can think about this when we're working with spatial data. Of course, there's some graph bottlenecks to using graphs. For example, the number of edges explodes very quickly. In other words, let's say that you have 1 million pixels and you want to represent k-nearest neighbors with graph edges. So you're going to have billions of edges now. So this is going to be a very large data representation. So being able to represent this effectively is important. That's not good. I think I got some. I don't know what happened there. So just to show you an example. So this is what we mean with the regionalization problem, where we have some underlying data that we want to create these spatially contiguous clusters. What you're looking at here is the map of Uruguay, and we have temperature data. We just want to create similar temperature regions. But so this is much different than what you might be used to with k-means or TSNE, right? So when we are creating clusters, spatial proximity is important. We have to create regions. They cannot be pixelated all over the place. So when we talk about graph-based representations, going back to your question, we can have data. So these are the municipal districts in Uruguay, different polygons, and I have some values observed in them. So this already is a hard problem to represent. Because first and foremost, one great thing with CNNs that brings people like me and Felipe here who work on earth science, on earth observations, is CNNs are inherently spatial, whether we like them or not, because you have a convolution, you have a filter that spatially rolls over the image. Now, that doesn't really work when you have vector data with irregular sizes, areas. There are some regions in Uruguay that are so big that you can slide a window over and you can still be in the same data point. Whereas there are some very small ones where the same slide can give you tens of neighbors. So how do you resolve that? You can unify this with a graph where you can represent every spatial location with a vertex, the red points there. And if there is a conceptualization of neighborhoods, for example, if you consider a neighbor that shares an edge to be a neighbor right next door, you can connect them with lines. So that's how you create this graph. So this is a simple graph representation. This is what we call a clean contiguity graph representation of the data. And going to this representation, again, what you're looking at on your left, it changes the learning problem. So when we think about clustering, what we're talking about, if you think about a Lloyd algorithm, we start with some core points, and then we move those core points until elements that are attached to those cores are as different as possible. But when you have a graph data set, this changes the problem a little bit, this representation. Now we are actually in what we call a pruning game. In other words, we need to cut some edges off this graph so that we create these subgraphs that are that consist of very similar elements. So this changes the problem. So one of the very important mathematical tools here are trees, also spanning trees that we use a lot in spatial unsupervised learning. We can take a very dense graph where we have to parse through all these graph edges and reduce it with a spanning tree. You can think of this as connecting the dots. You basically only keep edges between the two most similar elements. And you come up with this tree. And one mathematical property of this is you don't have any closed loops. And you traverse all of the graph elements. And now we're looking at our clustering problem becomes finding these optimal edges to remove so that we can define these subtrees that are graphs. So this is the clustering problem. But as you see, the spatial twists makes this problem much different. So coming back to the question of ontologies, representations, graphs are very powerful ways of representing spatial data, because they allow us to solve spatial problems. So this is the end result once we remove those edges from the trees. And we can basically play around with different parameters like number of clusters. This gives us these clusters that are all spatially contiguous. The results for k-means is much different than this. Its colors are just all over the place because there is no concept of contiguity. So this is what we call a tree-based regionalization. Basically represent every spatial unit with points, depending on the neighborhood conceptualization, connect them, and then remove edges, create a tree, then remove edges between dissimilar elements until we come up with subtrees that represent different clusters. And very similar to the Loy's algorithm, we do that by looking at standard deviations. We basically want to minimize the deviation within a cluster and maximize it between different clusters. So that's how we pick which edges to remove. So we did this to create temperature regions in contiguous United States. We accumulated data at the county level. So this is 2 meter resolution simulated temperature from a global climate model, like the ones that is used in the Climax model that Felipe mentioned. This is for the March of 2022. We just aggregated temperatures. Darker color means hotter. And what I want to do is I want to create temperature regions, purely data driven. I'm not going to use any climatological information other than the data, but I want to acknowledge the fact that the regions need to be spatially contiguous. So this is the k-means result. As you see, there are patches everywhere. But the data, there's already some spatial autocorrelation that already shows you this north-south stratification, right? But we can't really resolve areas, especially Colorado is very hard, right? You have the mountains, effect of the mountains. You have very big differences. So it creates a lot of patchiness in this area where the temperature shows a lot of variation. So we cannot resolve this with a non-spatial method. But when we use the method I just mentioned, this is something that we developed where we are using trees. You see that the result is contiguous. Now we are able to define regions when we connect the data this way. We can also think about defining probabilities, and this is a recent paper we published. Basically, the clustering problem is an optimization problem, and when you are imposing constraints on an optimization problem, that means that your search space is much narrower. In other words, you're probably missing better clusters by imposing that they need to be contiguous, they need to be neighbors, right? You might probably be able to create more homogeneous regions if you don't have to impose that they need to be regions or contiguous. So we assess the impact of this constraint by clustering probabilities. So the lighter colors means that low cluster probability. In other words, that spatial unit can flip over clusters very easily if the data was perturbed. And no surprise at all, those ones generally exist at the peripheries of the clusters where it already has a border and it's easy to switch. And we can see the impact of, it will come back. we can see the impact of the spatial constraint on the result. So this is what we mean with fuzzy regionalization, where we can create these probabilistic estimates. So this is just an example of a type of spatial machine learning regionalization problem, but I want to talk briefly about this. I'm glad that ontology came up at a great time, but this is not what I call an ontology. This is just a numerical representation of spatial information. So spatial ML methods are being developed in parallel to a lot of non-spatial methods like CNNs, deep neural networks being applied to spatial data. But going back to the ontology, one keyword I would leave you with is the knowledge graphs, which is, I would say, one of the biggest undertakings in geography since GIS. There are multiple labs working on this, where the idea is to connect spatial information with very large graphs like this, so that you can query things like even something non-spatial, like an event, like the news, using geographical commands and information. So this is a huge undertaking in terms of representation. So if there are no questions about what we discussed, we can move on to our application segments.
Just a quick question.
Yes.
So part of the tree-based regionalization is to be continuous. That's the constraint. that you
Yes.
can have with. And so if we look at the map of the United States, let's say, we're like, where it's in, let's pick up an area in California, let's say in the middle there, that temperature matches, for example, Michigan. Is that line gonna keep continuing there, or how are we dealing with that at that point?
So that's why we use the sum of deviations. What we basically look at is, so when we create a cluster here, everything that's connected with a white line, they're in the same group. So we assess how much variability is there in that group compared to all the other groups. So if you connect, say, San Bernardino County in California to Ann Arbor, you're probably going to create this like huge lanky tree that crosses half of the country, right? The SSD there, the deviation is going to be very high, which is going to result in a low quality cluster because there's a lot of variation. With clustering, our whole goal is to reduce variation by creating homogeneous groups in the data. So this is how that will be learned by the model.
Awesome. And the second quick question is like, one part of it is also you could say, oh, I want 2 clusters, I want 10 clusters.
Yes.
So, I mean, can we let the model pick how many clusters? Like, would that be part of it instead of dictating how many?
Yeah, so the part of the work we do here, we actually use something non-spatial. We just use the AIC between different clusters. Like we basically track the quality of the clusters. Actually, we use something very similar to like the elbow curves. I'm sure you've seen those in clustering models. So you can use things like silhouette index, because after the clusters are defined, I did not mean to say AIC. This is for supervised learning. I meant mutual information. So we look at mutual information. In other words, we look at like how different groups are and how similar the groups are. So we can simply quantify that and test that for a different number of clusters and basically pick the best one.
Great work, thank you.
Mm-hmm. Here.
I have what they already opened that slide was the one that I had.
I'm just going to restart it. I'm just going to run off because they're just going to take a while.
It'll go fast, like 5 minutes. That's it. It was this. So from my end of this one of the final things I would like to mention is looking more about the pipeline when we do this analysis of Earth observation data to do mapping, such as sometimes we get requests for mapping entire regions or maybe the entire countries. How do we go about that? Because training your model is just one part of it, right? So using as example, this part of building footprint mapping, that's something that we do in this context of like population mapping, for instance. When we think about our pipeline, there are different components that we need to consider, right? You get first a request like, can you cover area X? Starts with, do you have data for that? Does that data fit in what your model can handle in terms of like the spatial resolution, your cloud coverage, and so on? Once you have that, okay, cool. Let's deploy our model, see what we have already in-house that is suitable for that. And then you see that maybe this new area has some combination of like some desert or some mountains that maybe undergone some snow coverage that the model has never been exposed to. So you're like, okay, I'll need to do some extra fine tuning. So you need to go about doing more annotation about that specific area. So we try to operate then for this type of problems like the building footprint model that we already have in place under this sort of active learning approach of looking where you have a model, deploy the quality, what you get. And when you have to do a fine tuning, have some diversification criteria, whether you look at the geolocation or some of the embeddings that you can get from your pre-training model. And then trying to facilitate as well the work of the folks doing the annotation, because this can be very intense if you're looking at let's say a dense urban area, try to label all the buildings. So instead of what we can try to put in place are ideas of like, here's the current model output, highlight to me which ones are wrong and fix those instead of re-annotating the whole thing. So those are some considerations to think when you think about deployment pipelines for this type of data that is important to keep in mind. The other part to highlight is, again, our final product are those vector maps. So when you look at the first step of vectorization, you see this kind of very irregular shapes that when you start to talk with people like that they want to make use of this data, it becomes a major trustworthiness issue because they look at it and say, this doesn't look like buildings. So you can have maybe the even like a better intersection over union at pixel level of that version, but that's much less appreciated or less trustworthy than when you have some corrections of your vector shapes and some filtering of false negatives that are super small kind of thing for your final product quality. And then it touches the aspect that those images are huge. You cannot simply take for granted that you can put a big batch into your GPU and process everything in parallel. You rather need to think about how you do the tiling. So you split your big image into blocks, suppose like 1024 by 1024 pixels. You need to be careful that you have some overlap in between those when you're doing the stride, because otherwise you create artificial boundaries that can become like false negatives in your detection modules. Or you can create discontinuities on your structure that actually don't exist. And then you need some tools for this kind of synchronization, this management across maybe different GPUs or different machines, different nodes. For quite a few years, we were working, for example, with Spark as one of these tools. More recently, we're now playing with Dask. That's one tool that I would point you to if you're interested in doing, particularly more thinking about inference side of models that you want to deploy over large volumes of data and coordinate this process across different machines. Dask has some cool stuff, including some Jupyter notebooks, Colab things with PyTorch. So you can easily get up to speed with that and start playing with it. So that's one of the things that I wanted to show you. And then the other example I just want to mention a bit is how you think about problems like, for example, if you're trying to do damage assessment, regardless of what kind of damage it is or what area it is. You can start a problem of like you have maybe very large areas that you want to deploy a model or cover there. How do you start to look at where exactly is more likely that we saw damages for both labeling data and deploying your model? So there are resources out there, how I mentioned, for example, there is this United Nations sources of final data products, but also you have resources such as the Live UA website that gives you some points of where some events are happening, or you can rely on maps sometimes even of news outlets or anything that gives you some spatial information where you should be looking at. So again, it's not only about the images. And also when you define the problem, like how do you do about creating guidelines for the annotation? Because it can be very subjective sometimes when you're talking about levels of damage. Like one of the things we try to build upon is of course things that are already out there. For example, the material guidelines from FEMA. But then these guidelines, they do not consider that you only have image from above. You might have a guideline saying like, well, you have this level of damage if you have a crack in the facade. I cannot see the facade. So you need to do some conversions and you need to interact with the folks doing the annotation. Because you can think like, maybe I'm gonna add like another field for them to put their level of uncertainty. If you start putting too many choices, it becomes more stressful, the work, and more like varies much more to the point that you have less reliability in your label data and less efficiency in the labeling process. And this part of efficiency of the labeling process then also comes into play stuff. Trying to leverage what you already have in hand. Like in our case, we can think about leveraging your building footprint mapping models that you already have. So you don't need to retrain something from scratch just for the damage assessment. You'd rather use this model for the pre and post event imagery, look at internal representations, and just train a decoder head to assign damage levels to these building footprints. And from an annotation perspective as well, this is beneficial because you're just asking the folks to put the damage level that you think this structure has undergone, instead of having to draw the whole polygons of each individual structure. And then finally, here I'm borrowing one slide from Casey Richards, who is he was a keynote speaker of another event that we organized at the WACV, the Winter Application of Computer Vision at the beginning of the year. She was talking about from the perspective of folks like at American Red Cross, that she tries to do this approach of bringing these techniques for usage, for awareness, for guiding their work on the ground. And then there are plenty of challenges related to like she said, like you cannot expect folks to run their Jupyter notebook to get some inputs. They need to have like maps and data formats and stuff that are in the ways that they already have their softwares or resources that are already used to work with, because they're already under pressure. You do not put like more things that are complicated for them to use. And you cannot put things that cost a lot for them to use either, especially if you're thinking about humanitarian type of efforts. And also, like, again, this aspect of like you need to have ways of quantifying uncertainty. You have to have ways of describing what the model is doing, at least in a way to have the trustworthiness and being able to use, because you cannot expect people to be AI experts to be able to use those tools. So I already covered those bases of the resources. So only one quick thing I want to mention before, or that is another application. Just other resources for you guys to take a look at is in particular the community that you have around remote sensing. So the GRSS has plenty of journals that you can look at if you want to publish stuff on that, and if you want to get like good material to learn more about it. So you have the IEEE GRS, that are more longer journals, you have letters, you have spatial topics. Strongly encourage you to look at that. And many other events that we have been doing, they're particularly the image analysis and data fusion. We have, by a bad coincidence, was today as well, the Earth Vision workshop that some collaborators have been organizing for multiple years already, CVPR. I think we cover different bases, more like giving the background, such that maybe next year or so, you guys are still interested in that, doing more plant stuff, and maybe you want to publish or get more into the techniques, go towards Vision, keep an eye on that for the next CVPRs. Also, you know, CLR, the WACV, BMVC, we are having presence, whether us or some collaborators. So there's plenty of cool stuff for you guys to look in terms of IEEE things. And also there is the ACM6 Spatial and the ISPRS are other types of resources that I encourage you to look at to get more into this field.